James Webb just stared into a galaxy thought to be dead and quiet, but what it revealed has scientists completely stunned. Stars forming where they shouldn't, energy surges in unexpected places. This dead galaxy is anything but the original classification, dead on paper. In the universe, galaxies are the sprawling metropolises of stars, gas and dust, each carrying the history of billions of years of cosmic evolution. Among these, some galaxies are labelled active, ablaze with the birth of new stars, blazing with ultraviolet light and cosmic fireworks. Others, by contrast, are considered dead, or more precisely, quiescent, a term astronomers use to describe galaxies where the processes of star formation have all but ceased. But what does it truly mean for a galaxy to be dead? And how did astronomers come to classify some of these colossal structures as no longer capable of producing new stars? At its most basic level, a quiescent galaxy is one in which the gas necessary to form new stars is either absent or rendered inactive. Stars are born when dense clouds of cold molecular gas collapse under their own gravity, igniting nuclear fusion in their cores. In quiescent galaxies, this star-forming fuel is either depleted, dispersed, or heated to temperatures that prevent collapse. Without this raw material, the galaxy cannot sustain the process that has shaped the majority of its structure and luminosity. In other words, a quiescent galaxy is no longer actively shaping its stellar population. Its existing stars age, burn through their fuel, and die, leaving behind a population dominated by old, red, and often massive stars. The classification of a galaxy as quiescent comes from decades of observational astronomy, stretching back to early surveys that used visible light telescopes to map the sky. Initially, astronomers relied on simple photometric measurements, galaxies that emitted less blue and ultraviolet light, the signature of young, hot stars, were flagged as potential quiescent systems. Over time, these classifications were refined using spectroscopic surveys, which allow scientists to analyze the light from galaxies in terms of its constituent wavelengths. Spectra reveal not only the ages of stars, but also the chemical composition of the interstellar medium, the presence of gas, and whether the galaxy exhibits emission lines indicative of ongoing star formation. A crucial characteristic of a quiescent galaxy is the absence of detectable star formation. This is not a casual observation, but one confirmed through multiple independent lines of evidence. First, astronomers examine ultraviolet light, which is emitted by massive, young stars with lifespans of only a few million years. A galaxy devoid of this UV signature is unlikely to be forming new stars at any meaningful rate. Next, they probe for emission lines such as H-alpha, the spectral fingerprint of hydrogen atoms ionized by newborn stars. If H-alpha is absent or extremely weak, it indicates that the processes fueling star formation are no longer active. Finally, infrared observations, which can detect star formation hidden behind dust clouds, provide a further check. In quiescent galaxies, even these infrared signatures are minimal or non-existent, cementing the classification. But the lack of star formation is only part of the story. Quiescent galaxies are also marked by depleted reservoirs of cold gas, the molecular clouds that are the cradles of star formation. Observations using radio and submillimeter telescopes reveal the presence or absence of molecular gas such as hydrogen, H2, and carbon monoxide, CO. In a truly quiescent galaxy, these clouds are either absent or so diffuse that they cannot collapse to form new stars. This contrasts sharply with star-forming galaxies, where dense, cold molecular clouds are abundant and continuously replenished. The depletion of cold gas is a critical signal that the galaxy has undergone a transformative process, whether through internal mechanisms like supermassive black hole feedback or external environmental influences such as ram pressure stripping in galaxy clusters. The stellar populations of quiescent galaxies tell another part of the story. Unlike galaxies dominated by young blue stars, quiescent systems are primarily populated by old red stars that have existed for billions of years. These stars exhibit a range of ages, but the absence of significant populations younger than a few 100 million years is telling. Stellar population synthesis models allow astronomers to determine the age distribution of stars in a galaxy by analysing its integrated light. These models rely on precise measurements of colour, absorption lines, and luminosity. When applied to quiescent galaxies, they consistently reveal that the bulk of star formation occurred in the distant past, often within the first few billion years of the universe's existence, with little activity thereafter. The processes that lead to quiescence are varied and remain a major focus of astrophysical research. Internal mechanisms include feedback from active galactic nuclei, where energy released by a central supermassive black hole heats or ejects gas, preventing new stars from forming. Supernova explosions can contribute, injecting energy into the interstellar medium and disrupting molecular cloud. Environmental effects also play a role. Galaxies in dense clusters can have their gas stripped away by the hot intracluster medium, a process known as ram pressure stripping, or they can be dynamically disturbed by gravitational interactions with neighbouring galaxies. Each of these mechanisms leaves subtle traces in the galaxy's structure, kinematics, and chemical composition, which astronomers can detect with high-precision instruments. Observationally, quiescent galaxies exhibit a suite of typical signatures that make them stand out in surveys. One of the most obvious is their red colour. Unlike star-forming galaxies that appear blue due to the dominance of hot, short-lived stars, quiescent galaxies are dominated by older, cooler stars that emit most of their light at longer wavelengths. This red colour is not only visible in optical observations, but is even more pronounced in the near-infrared, where the light from these ancient stars is strongest. The red colour serves as a first-pass indicator for astronomers, signalling a galaxy's potential quiescence even before detailed spectroscopic analysis. Another hallmark is the weak or absent emission lines in their spectra. Emission lines are created when gas is ionized by energetic processes, typically young stars or active galactic nuclei. In quiescent galaxies, these lines are either extremely faint or completely absent, reflecting the lack of ionizing sources. The absence of emission lines is a key diagnostic criterion, helping astronomers distinguish truly inactive systems from galaxies that might appear red due to dust obscuration, but are still forming stars. Structurally, quiescent galaxies often present as smooth, elliptical systems. Unlike spiral galaxies, which display prominent arms, clumps, and active star-forming regions, quiescent galaxies typically have a spheroidal or elliptical morphology. Their light distribution is uniform and centrally concentrated, lacking the patchiness and filamentary structures associated with young stars. High-resolution imaging from telescopes like Hubble has revealed that many quiescent galaxies at both low and high redshift possess these smooth profiles, with little substructure, which reinforces the classification. Taken together, the lack of star formation, depleted cold gas, old stellar populations, red colours, absent emission lines, and smooth structure, these indicators form a coherent picture of what astronomers call a quiescent galaxy. The classification is not superficial. It is the result of decades of multi-wavelength observations, sophisticated modelling, and careful cross-checks with theory. When astronomers look at a quiescent galaxy, they are essentially seeing a fossil record, a snapshot of a system that has ceased evolving in the ways most galaxies do. It is against this backdrop that the James Webb Space Telescope entered the story. For years, astronomers relied on the dead classification to guide their models of galaxy evolution. Quiescent galaxies were treated as the final stage in a galaxy's life cycle, a period of quiet, predictable decline after a period of active star formation. They were assumed to be simple, unchanging, and relatively uneventful, their physical properties well understood and largely accounted for in simulation. JWST was initially tasked with observing them for precisely this reason: to confirm theories, to refine models, and to add detail to the timelines of galaxy quenching. Yet, as we now know, the story was far more complicated than anticipated. Even the most meticulously classified quiescent galaxies can hide surprises, and JWST, with its unparalleled sensitivity and infrared capabilities, was poised to reveal them. By peering deeper into the light of these so-called dead galaxies, it could detect the faintest whispers of star formation, the hidden reservoirs of gas, and the subtle structural irregularities that had eluded earlier telescopes. In doing so, JWST would challenge long-standing assumptions and force astronomers to rethink the very meaning of dead in a cosmic context. The original classification, dead on paper, was never meant to imply absolute inactivity. It was a working definition, a shorthand for a galaxy that no longer displayed the dominant hallmarks of star formation visible with previous instruments. But as with any classification based on limited observations, it was vulnerable to revision. JWST's observations would demonstrate that quiescence is not always permanent, that galaxies once thought to be past their star-forming prime can harbour secrets waiting to be uncovered, and that the universe still has surprises in store, even in places where astronomers assumed the story had ended. The typical signs of a dead galaxy. When astronomers talk about a dead galaxy, they are not using poetry, they are using evidence. Every galaxy has a story hidden in its light, in the colours it shines, the lines in its spectrum, and the shapes it forms across the sky. Quiescent galaxies, the so-called dead galaxies, have a set of fingerprints that make them easy to spot, if you know what to look for. These fingerprints are the reason astronomers thought they understood these galaxies so well, and why the discoveries by the James Webb Space Telescope felt like opening a book only to find secret pages hidden between the lines. The first and most obvious signature of a quiescent galaxy is its red colour. Unlike young, active galaxies, which glow with the bright blues and ultraviolet light of massive new stars, quiescent galaxies appear reddish. This redness comes from old stars, stars that have already burned most of their fuel and have cooled. These stars dominate the light we see, drowning out any faint blue glow from occasional new stars. The effect is so strong that in large surveys of the sky, astronomers could separate galaxies into blue and red populations almost instantly. Blue galaxies were busy making stars. Red galaxies were assumed to be quiet and settled. Redness alone, however, is not enough to call a galaxy dead. Dust can also make a galaxy appear red, even if it is actively forming stars. To confirm quiescence, astronomers look deeper at the galaxy's emission lines. Emission lines are the fingerprints of gas in the galaxy, glowing in specific colours because it is energized by young stars or other processes. In star-forming galaxies, the hydrogen gas produces bright H-alpha lines, neon and oxygen lines light up, and the galaxy spectrum is full of activity. Quiescent galaxies, by contrast, show very weak or almost no emission lines. This absence signals that the energetic processes that light up gas, mainly massive young stars, are missing. Without these lines, astronomers are confident that the galaxy is not making new stars at any significant rate. The next sign is structure, the shape of the galaxy itself. Most quiescent galaxies are elliptical, with smooth, rounded shapes and no visible spiral arms. Star-forming galaxies are messy, clumpy, patchy, filled with bright knots of young stars and dark lanes of dust. Quiescent galaxies, in contrast, have a uniform light distribution. High-resolution images from telescopes like Hubble show these galaxies as serene spheres or slightly stretched ellipsoids, like cosmic clouds frozen in place. The smooth shape reflects a long history of dynamical settling. Over billions of years, interactions, mergers, and the death of young stars can smooth out the structure, leaving behind a calm, featureless galaxy. This combination, red colour, weak emission lines, and smooth elliptical structure, has been so reliable that astronomers have used it for decades to classify galaxies. Surveys across the sky, From the Sloan Digital Sky Survey to the deepest Hubble imaging campaigns relied on these signals. Galaxies that ticked all the boxes were labelled quiescent. Their numbers were counted, their masses measured, and their evolution mapped. It became a cornerstone of our understanding of the universe. Blue galaxies are alive, red galaxies are dead. Yet, as straightforward as it seemed, this system hides complications. Red colours can be misleading. A galaxy might appear red because dust blocks the blue light, not because it lacks young stars. Weak emission lines could be hidden by the sensitivity limits of older instruments or drowned out by background noise. And even smooth galaxies can harbour small regions of activity, undetectable unless viewed with the right tools. Until now, these subtleties were invisible. Quiescent galaxies seemed simple because telescopes could only see the broad strokes. The devil, as it turns out, was in the details. Enter the James Webb Space Telescope. JWST's infrared eyes can pierce dust, reveal faint gas emissions, and see the older stars more clearly than ever before. When astronomers pointed it at a galaxy previously classified as dead, the first surprise came in the light itself. The red colour, once taken as a marker of inactivity, turned out to hide small pockets of younger stars. These stars were faint and swamped by the glow of the older population, invisible to previous instruments. JWST could separate the layers of starlight, showing that even galaxies thought to be finished making stars were quietly still at work. Then came the emission lines. Where ground-based telescopes and Hubble had seen nothing, JWST detected faint hydrogen and oxygen light. These signals indicated ionized gas, the fingerprint of star formation. Even in a galaxy billions of light years away, light from tiny clusters of newborn stars had survived the journey to Earth. It was enough to overturn the classification. A galaxy previously labelled dead was not fully dead. It had not gone entirely silent. It had merely whispered its activity in frequencies older telescopes could not detect. The structure too told a different story. JWST's high-resolution imaging revealed subtle clumps and irregularities inside galaxies thought to be perfectly smooth. Small star-forming regions, pockets of gas, and tiny dust clouds had gone unnoticed. The seemingly calm, elliptical shape of quiescent galaxies was in reality a mask hiding ongoing activity. Elliptical galaxies were not entirely featureless. They were camouflaged, appearing dead in optical light while quietly evolving in infrared. Taken together, these findings forced astronomers to rethink what dead really meant. Red colour alone is no longer sufficient. Smooth elliptical structure may hide irregular, ongoing processes. A galaxy that looks inactive in one wavelength may be surprisingly alive in another. JWST has demonstrated that our universe is more complex, more nuanced, and more full of surprises than previously imagined. The implications stretch beyond a single galaxy. If one supposedly dead galaxy can harbour hidden star formation, how many others do the same? Surveys that counted red smooth galaxies as quiescent may have underestimated the number of galaxies still quietly forming stars. Models of galaxy evolution, star formation histories, and the cosmic timeline itself may need revision. What once appeared simple and settled is now a puzzle with hidden layers, challenging decades of assumptions. JWST has opened a new window on the life of quiescent galaxies. Red colours are no longer absolute indicators of inactivity. Weak emission lines may hide faint but ongoing star formation. Smooth elliptical structures can conceal irregular, subtle processes that were previously invisible. What astronomers once classified as dead is in reality more dynamic, more alive, and more mysterious than anyone could have guessed. Why this galaxy was ignored for years. In the cosmos, countless galaxies drift silently, each a massive collection of stars, gas, and dust, shaped over billions of years. Some galaxies explode with activity, their newborn stars shining bright, ultraviolet light blazing across space. Others, in contrast, appear quiet, unremarkable, as if they have long since stopped creating new stars. It is in this category that astronomers once placed the galaxy at the heart of our story, a galaxy considered uninteresting, even dull, by the standards of cosmic discovery. For decades it was ignored, buried in the catalogues of surveys, overlooked in favour of galaxies more dramatic, more luminous, more alive. The first reason this galaxy went unnoticed lies in previous observations, primarily from the Hubble Space Telescope and a range of ground-based surveys. Hubble, with its optical and near-infrared cameras, has revealed some of the most spectacular images of the universe ever captured. It has traced the sprawling arms of spiral galaxies, exposed the dense cores of massive ellipticals, and mapped galaxies billions of light-years away. Ground-based telescopes, equipped with large mirrors and advanced spectrographs, have complemented this work, providing spectra that reveal the ages of stars, the presence of gas, and chemical compositions across the galaxy population. Yet even with these tools, this particular galaxy seemed to offer nothing new. Its light was red, smooth, and quiet. It lacked the bright blue regions that signal the presence of young stars. It displayed no dust lanes twisting across its face. Its centre appeared calm, without the telltale glow of an active nucleus. To every observer scanning the sky with these instruments, it was simply a typical quiescent galaxy, a fossil from an earlier era of star formation, a cosmic relic destined to fade into obscurity. In the optical images, the galaxy's red colour dominated its appearance. Unlike galaxies bursting with star formation, whose young, massive stars shine in brilliant blues and ultraviolet light, this galaxy's light was warm, red, and smooth. There were no knots of bright stars clumped along spiral arms, no flickers of energetic stellar nurseries hidden in dust clouds. To the human eye and to earlier detectors, the galaxy appeared calm, static, and uneventful. It was the cosmic equivalent of a quiet countryside town, its streets empty, its lights dimmed, in a universe full of bustling star factories. Even Hubble's sharp imaging revealed no dust lanes, the wispy ribbons of cold gas and dust that thread through many galaxies and serve as the raw material for new stars. Dust lanes are like fingerprints of activity. They absorb starlight, glow in infrared, and often indicate regions where stars are forming. In this galaxy, no such lanes were visible. Its light was uniform, with no obscured clumps hinting at hidden processes beneath the surface. The lack of dust suggested that the galaxy had either consumed its star-forming fuel long ago or expelled it, leaving behind a simple, smooth, stellar population. The galaxy's centre, too, appeared ordinary at first glance. Many galaxies harbour active galactic nuclei, bright central regions powered by supermassive black holes consuming gas and dust. AGNs are among the most energetic phenomena in the universe, lighting up galaxies with X-rays, ultraviolet, and infrared emission. But early observations found no evidence of a bright core, no obvious signs of a black hole feeding actively, no emission lines screaming for attention. To astronomers using Hubble and ground-based instruments, the galaxy's nucleus seemed dormant, further reinforcing its classification as unremarkable. Taken together, these characteristics, the red colour, the smooth structure, the lack of dust lanes, and the apparently inactive nucleus, made the galaxy uninteresting by traditional survey standards. With millions of galaxies to observe, scientists naturally prioritise the ones with dramatic features, galaxies forming stars at furious rates, merging galaxies with distorted shapes, and AGN hosting systems radiating powerful energy. This galaxy was ordinary. It was quiet. It was assumed to be well understood. In the vast catalogues of Hubble and other surveys, it was just another red dot in the sky, not a candidate for a major discovery. And yet, despite appearing unremarkable, this galaxy did end up on the target list of the James Webb Space Telescope, a telescope designed to uncover the secrets of the universe at unprecedented depth and clarity. How did a galaxy considered boring for decades suddenly become worthy of one of the most valuable observation slots in modern astronomy? The answer lies in the way JWST's observing programs are designed, with goals that go beyond the obvious and into the realm of calibration, statistical surveys, and control samples. First, JWST observations require calibration targets. Every instrument on the telescope must be finely tuned, tested, and benchmarked before it can produce reliable scientific data. Bright, well-understood objects, including certain quiescent galaxies, are ideal for this purpose. They provide stable references against which the telescope can measure sensitivity, instrument response, and background noise. This galaxy, though seemingly unremarkable, offered a perfect calibration target. Its light was smooth, predictable, and free of unexpected emissions that could complicate tests. In this sense, JWST was not sent to look for fireworks. It was sent to check its own instruments, and the galaxy happened to fit the bill. Second, the galaxy was part of High Redshift Quiescent Galaxy Studies, a scientific program aimed at understanding how galaxies stop forming stars over cosmic time. Quiescent galaxies at high redshift, those formed when the universe was much younger, offer critical clues about the processes that shut down star formation. Astronomers need examples of galaxies that appear dead, so they can compare them to active galaxies of similar mass, age, and environment. Even if a galaxy seems dull in visible light, it may hold vital information about the evolution of galaxies billions of years ago. This particular galaxy, located at a high redshift, was valuable precisely because it seemed ordinary. Its apparent inactivity allowed scientists to test their models of quenching and galaxy evolution. Finally, it served as a control sample for galaxy evolution research. In science, controls are essential. To understand change, you must first understand stability. By observing galaxies classified as dead, astronomers can determine baseline properties for galaxies with little to no star formation. These control samples allow comparisons with galaxies that are forming stars, merging, or undergoing other dynamic processes. Without controls, it is impossible to separate the effects of environment, mass, or cosmic age on galaxy behavior. This galaxy, though quiet and unassuming, provided that critical baseline, a benchmark against which more active galaxies could be measured. The galaxy was both ignored and important. It was ignored in earlier optical surveys because it lacked dramatic features. Yet it became important for JWST because of its predictability, its role in testing theories, and its value as a reference point. This duality illustrates how science operates. Sometimes what appears mundane with one set of instruments becomes revolutionary with another. What was once overlooked can suddenly become central to understanding the universe, not because the galaxy itself changed, but because our ability to see it changed. The irony is that this galaxy, considered boring for decades, would soon shock astronomers in ways that no one could have anticipated. Its apparent simplicity, its lack of blue light, dust lanes, or an active nucleus had masked secrets waiting to be revealed by JWST's infrared vision. The quiet, unremarkable red dot in survey catalogues would turn out to harbour unexpected gas, hidden star formation, and subtle structural features, rewriting the story of what it means to be a dead galaxy. JWST's selection of this galaxy demonstrates a critical point about scientific observation. Sometimes, the most important discoveries come not from the brightest, most obvious objects, but from those that have been quietly hiding in plain sight. The galaxy's path from obscurity to the focus of a cutting-edge telescope illustrates how astronomers design observations not only to chase the spectacular, but also to uncover hidden truths, to test assumptions, and to explore the boundaries of the known universe. How it ended up on JWST's target list. Even though this galaxy looked inactive, it became a target for the James Webb Space Telescope because of the way JWST selects its observation targets. Telescopes do not only observe the most dramatic objects, they also observe galaxies that are useful for testing instruments, understanding galaxy evolution, and comparing different types of galaxies. This galaxy fell into all of these categories. One of the main reasons it was chosen was calibration surveys. Every new telescope needs objects that are well understood to make sure its instruments are working correctly. JWST's cameras and spectrographs need reference points for brightness, colour and spectrum. Galaxies that appear quiet and simple, like this one, are ideal for calibration because their light is predictable. Observing them allows scientists to check that the telescope's measurements are accurate, that the detectors respond correctly, and that any data errors can be identified. In this case, the Galaxy provided a stable benchmark to test JWST's performance. Another reason it was selected was for high redshift quiescent galaxy studies. Scientists are very interested in galaxies that stopped forming stars in the early universe. Understanding when and how galaxies stop making stars is a central question in astrophysics. This galaxy is located at a high redshift, meaning we see it as it was billions of years ago. At that time, the universe was younger, and many galaxies were still forming stars rapidly. Galaxies that had already stopped forming stars at that stage are rare. By observing this galaxy, astronomers could study a population of early quiescent galaxies to understand how star formation shuts down and how these galaxies evolve over time. High redshift quiescent galaxies are especially valuable because they provide a comparison to active galaxies of similar mass and size. By comparing the properties of dead galaxies to active galaxies at the same epoch, scientists can see how processes like gas depletion, mergers, or black hole activity influence galaxy evolution. Even though this galaxy looked uninteresting in visible light, it was part of a carefully chosen sample to answer these big questions about how galaxies evolve. The galaxy also served as a control sample for galaxy evolution studies. In scientific studies, control samples are used to provide a baseline for comparison. Observing galaxies that appear inactive allows astronomers to compare them to galaxies that are forming stars, merging, or otherwise active. Control galaxies help identify what changes are linked to star formation and what is simply the natural background of galaxy properties. This galaxy, classified as dead, provided that baseline. Its data could be compared to active galaxies to measure differences in gas content, stellar populations, and structure. Without such control samples, it is difficult to interpret observations of active systems or understand the sequence of galaxy evolution. JWST's instruments made it possible to collect data on this galaxy that were impossible to gather with previous telescopes. Its infrared cameras can detect light from older stars, from dust-enshrouded regions, and from faint emission lines. The spectrographs can measure chemical composition, gas velocity, and star formation rates even in very faint regions. Observing a quiescent galaxy with these instruments allows scientists to test predictions from models about how galaxies stop forming stars, how gas behaves in the absence of star formation, and whether dormant galaxies are truly inactive or just appear so in optical light. Additionally, JWST observation programs are often designed to include a mix of target types: active galaxies, quiescent galaxies, and objects of unknown classification. Including galaxies that appear dead ensures that scientists are not only testing extreme cases of activity, but also verifying how well models explain systems that are assumed to be simple. Even a galaxy that looks uninteresting can provide critical information because it allows astronomers to test the accuracy of classification methods, refine measurement techniques, and identify unexpected features. The selection process also considers redshift coverage. Scientists want to understand galaxies at different points in the universe's history. Quiescent galaxies at high redshift are rare, so even if a galaxy appears inactive, it is valuable because it represents a time period that is not well sampled. Observing multiple high redshift quiescent galaxies allows astronomers to build statistical samples, measure trends, and understand whether the processes that stop star formation were common or unusual in the early universe. This galaxy fit that requirement. Another factor was comparison to simulations. Modern astrophysics relies heavily on simulations that model galaxy formation and evolution over billions of years. These simulations predict how galaxies of different types should appear, how their gas content should change, and when they should stop forming stars. Observing galaxies that are classified as dead provides a direct test of these predictions. If JWST finds features that were not expected, like hidden gas or faint star formation, scientists can compare these results to models and refine their understanding of galaxy physics. In this way, even a galaxy that looks boring can challenge existing theories. Finally, observing this galaxy contributes to long-term studies of galaxy quenching. Astronomers want to know whether quiescent galaxies remain inactive indefinitely or if star formation can restart. Selecting galaxies that appear dead allows JWST to collect detailed data that can answer this question. If hidden star formation or gas reservoirs are found, it could show that galaxies thought to be permanently inactive may actually have intermittent activity. Including this galaxy in JWST programs ensures that these possibilities are explored. Standard model of galaxy death. Galaxies form stars when they contain cold gas, mainly hydrogen, that can collapse under gravity to ignite nuclear fusion in stellar cores. Over time, several mechanisms can stop this process, producing galaxies that appear inactive or quiescent. Current astrophysical models describe this process in three main ways: gas exhaustion, active galactic nucleus feedback, and environmental stripping. Gas exhaustion occurs when a galaxy simply uses up the material needed to form new stars. Star formation is an ongoing process, with gas clouds collapsing into dense regions that produce massive stars. These stars burn through their fuel in millions to billions of years, returning some material to the interstellar medium through stellar winds and supernovae. Despite this recycling, the total supply of cold molecular gas can decline over time. In massive galaxies, this decline can be accelerated by high star formation rates during early periods, leaving little gas for future generations of stars. Once the gas is depleted below a critical threshold, new star formation slows dramatically or stops entirely, leaving the galaxy populated mainly by older stars. Active galactic nucleus, AGN, feedback is another major factor in quenching star formation. Many galaxies host supermassive black holes at their centers, which can accrete surrounding gas and release tremendous amounts of energy. This energy heats or expels gas from the galaxy, preventing it from collapsing into new stars. There are two main modes of AGN feedback. The first is the quasar mode, where rapid accretion produces powerful radiation and winds that push gas out of the galaxy. The second is the radio mode, in which relativistic jets from the black hole inject energy into the surrounding medium, maintaining high gas temperatures and suppressing star formation over long periods. The effect of AGN feedback is often strongest in massive galaxies, where central black holes can reach billions of solar masses. Environmental effects also contribute to galaxy death, particularly for galaxies located in clusters. As a galaxy moves through the hot intracluster medium, its gas can be stripped away through ram pressure stripping. This process removes cold gas from the galaxy's disk, leaving little fuel for new stars. Tidal interactions with other galaxies, including minor mergers or close flybys, can disturb gas distributions, heat gas, or expel it entirely. In some cases, these processes work together with internal mechanisms like AGN feedback to accelerate the cessation of star formation. Environmental stripping is especially important for satellite galaxies in clusters, which often show signs of rapid quenching compared to isolated galaxies of similar mass. The timeline of galaxy death in current models generally follows a three-step sequence. First, many galaxies experience a rapid starburst where gas collapses efficiently and massive numbers of stars form in a short period. Starbursts can be triggered by mergers, interactions, or internal instabilities that compress gas. During this phase, galaxies may shine brightly in ultraviolet and infrared light, and supernovae enrich the interstellar medium with metals. Starbursts consume gas at a high rate, often producing short-lived bursts of activity that last only tens to hundreds of millions of years. Following the starburst, galaxies undergo sudden quenching. Gas depletion, AGN feedback, or environmental stripping can rapidly halt star formation. Observationally, quenching is seen as a dramatic decrease in ultraviolet emission and the disappearance of strong emission lines associated with ionized gas. Models suggest that quenching can occur over a relatively short period, typically less than 1 billion years, for massive galaxies. The sudden drop in star formation produces a galaxy dominated by older stars, which gradually redden as massive blue stars die off. After quenching, galaxies enter a long passive phase. Star formation is minimal or absent, and the remaining stars age without significant replenishment. Galaxies in this phase are often massive ellipticals or lenticulars, with smooth, uniform light profiles. Their stellar populations are dominated by low-mass, long-lived stars that emit mostly red and infrared light. During the passive phase, the galaxy structure may continue to evolve through mergers, dynamical relaxation, or minor accretion. But these processes generally do not trigger significant new star formation. The passive phase can last for several billion years, effectively marking the final stage of the galaxy's life according to the Standard Model. Observational evidence supports this model. Surveys of the local universe show a clear separation between star-forming galaxies, which are often blue and clumpy, and quiescent galaxies, which are red and smooth. Spectroscopic studies reveal old stellar populations in quiescent galaxies, weak emission lines, and little cold gas. High redshift surveys indicate that massive galaxies formed stars rapidly in the early universe and then quenched quickly, consistent with predictions from models involving gas exhaustion and AGN feedback. Environmental effects, such as ram pressure stripping in clusters, are observed directly through gas tails and truncated disks. Simulations of galaxy formation also reproduce these behaviours. Cosmological models track the evolution of gas, stars, and dark matter over billions of years, including mechanisms like supernova feedback, AGN heating, and environmental stripping. Simulated galaxies show starburst phases followed by rapid quenching and extended passive periods. These models predict the mass, colour, and structure of quiescent galaxies in agreement with observations. They also suggest that the timing and effectiveness of quenching mechanisms depend on galaxy mass, environment, and central black hole properties. Gas exhaustion, AGN feedback, and environmental stripping are not mutually exclusive. Often, a combination of mechanisms drives quenching. For example, a galaxy may undergo a starburst that consumes most of its gas, while an active black hole prevents the remaining gas from forming stars. If the galaxy is in a dense cluster, ram pressure stripping can remove residual gas and accelerate quenching. These combined effects produce galaxies that appear dead within a relatively short period, matching observed properties of quiescent systems at various redshifts. The rapid starburst phase also leaves detectable traces in stellar populations. Massive stars formed during this period die quickly, producing supernovae that enrich the galaxy with heavy elements. The chemical composition of quiescent galaxies reflects this history, with higher metallicities in older stars compared to ongoing star-forming galaxies of similar mass. Absorption lines in spectra, such as magnesium and iron, provide evidence for these past starbursts and help date the quenching events. A GN feedback is similarly traceable. Even in galaxies classified as quiescent, remnants of past activity can be observed. Hot gas in the central regions, cavities or bubbles in X-ray images, and weak emission lines in infrared spectra indicate that supermassive black holes have influenced the galaxy's evolution. The energy output from these black holes is sufficient to heat or remove gas, preventing star formation even long after the black hole has stopped accreting actively. Environmental effects also leave clear marks. Galaxies in clusters often show asymmetrical gas distributions, truncated star-forming disks, or long gas tails pointing away from the cluster center. These features indicate that external forces have removed or redistributed gas, cutting off star formation. Observations with radio and submillimeter telescopes confirm that cluster galaxies have lower cold gas content than isolated galaxies, supporting the role of environmental stripping in quenching. The Standard Model also includes a prediction for the timescale of quenching. Rapid starbursts can last tens to hundreds of millions of years. Sudden quenching can occur in under 1 billion years for massive galaxies. The passive phase may continue for several billion years, depending on the galaxy's mass, environment, and subsequent interactions. This timeline matches observed color magnitude diagrams, stellar age distributions, and structural properties of galaxies across cosmic time. In the Standard Model, quiescent galaxies are not entirely static. Minor mergers, accretion of small satellites, or internal dynamical evolution can continue to reshape the galaxy's structure. However, these processes do not generally supply enough cold gas to restart significant star formation. As a result, galaxies remain dominated by older stars. Their color stays red, emission lines remain weak, and their overall structure appears smooth. Observations of high redshift quiescent galaxies provide additional support. Many of these galaxies form stars at very high rates in the early universe, exhausting their gas quickly. A GN activity and environmental factors then accelerated quenching. By the time the universe was a few billion years old, these galaxies had already transitioned to a passive phase. Their stellar populations, metallicities, and structural properties match predictions from the combination of gas exhaustion, AGN feedback, and environmental stripping. What JWST was supposed to confirm. The galaxy observed by JWST had been classified as quiescent for decades, and astronomers expected the telescope to provide a clear confirmation of this classification. Previous data suggested that star formation had stopped. The galaxy was dominated by old stars, and there was no significant molecular gas remaining. JWST's observations were planned to test these assumptions using its high-resolution infrared instruments, which can measure light from old stars, detect faint emissions from gas, and resolve structures that were previously invisible. The first expected outcome was a smooth infrared continuum. In quiescent galaxies, most of the light comes from old stars. These stars are cooler than young, massive stars, emitting primarily in red and infrared wavelengths. Previous observations in optical light showed a smooth distribution of light across the galaxy, consistent with an older stellar population. Infrared observations were expected to confirm this pattern, providing a cleaner view of the underlying stars without interference from dust or active star-forming regions. A smooth continuum would reinforce the galaxy's classification as inactive and show that the stellar population had reached a stable state. JWST was also expected to confirm old stellar spectra. Spectra provide detailed information about the ages, compositions, and temperatures of stars. In quiescent galaxies, spectra are dominated by absorption lines from older stars, such as red giants and low-mass main sequence stars. These lines indicate a lack of young, massive stars and provide a chemical record of past star formation. Astronomers anticipated that JWST's spectrographs would detect these absorption features clearly, showing no signs of young stellar populations, strong emission lines, or unusual chemical abundances. The spectra were expected to be consistent with stellar populations aged several billion years. Another key expectation was the absence of molecular gas lines. Molecular gas, primarily hydrogen molecules, is the raw material for star formation. In active galaxies, cold molecular gas emits at specific infrared and submillimeter wavelengths. Previous observations suggested that this galaxy had very little cold gas remaining, and JWST's instruments were expected to confirm this. Detecting molecular gas lines would indicate ongoing star formation or the presence of reservoirs that could fuel future stars. Since the galaxy was classified as quiescent, astronomers expected JWST to find no detectable molecular gas, reinforcing the notion that star formation had effectively ceased. JWST was not expected to reveal unexpected activity or hidden structures. Observing this galaxy was intended to confirm prior classifications, not to discover new phenomena. The telescope's sensitivity in the infrared was ideal for measuring properties that were already suggested by optical and ground-based data, such as stellar age, distribution, and chemical composition. The observation was designed to provide precise measurements of the galaxy's light, spectra, and potential gas content to strengthen the existing understanding rather than challenge it. The observation program focused on known properties of quiescent galaxies. The galaxy's smooth shape and lack of emission lines made it a suitable target for calibration and comparison studies. JWST's instruments were expected to validate earlier measurements, demonstrating that the galaxy's light was dominated by old stars, and that the distribution of light remained uniform in the infrared. No surprises were anticipated in either the continuum or spectral data. The telescope was also intended to check for faint structures in the galaxy that previous instruments could not resolve. While Hubble and ground-based telescopes had detected no dust lanes or clumps, JWST's higher resolution in the infrared was expected to confirm that there were no hidden star-forming regions. Any structures detected were anticipated to be minor and consistent with an aging, passive galaxy rather than indicative of ongoing activity. The observation program was planned as a controlled test of the standard model of galaxy death. Astronomers expected that JWST would measure the same features previously predicted: smooth infrared light from old stars, absorption-dominated spectra, and a lack of molecular gas. Confirming these properties would provide a benchmark for other studies, showing that quiescent galaxies truly have stopped forming stars, and that the mechanisms proposed for galaxy death, gas exhaustion, AGN feedback, and environmental stripping, produce the expected outcomes. Data analysis pipelines were designed accordingly. JWST was expected to produce high signal-to-noise images and spectra that could be compared directly to models. Absorption lines in the spectra would be used to estimate stellar ages and metallicities. Infrared continuum data would provide information on stellar mass and distribution. Any molecular gas detected above the sensitivity limit would have been considered unexpected, but the expectation was that no such lines would appear. JWST's selection of this galaxy also reflected confidence in prior surveys. Large-scale optical surveys, deep Hubble imaging, and ground-based spectroscopy had consistently shown that the galaxy was inactive. Infrared confirmation was considered a final check, providing higher resolution data and better sensitivity to older stellar populations. The telescope was not expected to overturn previous classifications, but to strengthen confidence in them. The choice of this galaxy illustrates how JWST's early observations were often designed to validate existing knowledge. By confirming properties of previously studied galaxies, astronomers could test the calibration of instruments, refine data processing methods, and ensure that the telescope produced reliable results across a range of targets. The expectation was that the data would reinforce the existing narrative of galaxy quiescence. A smooth light profile, old stellar spectra, and negligible molecular gas. JWST's instruments were optimized for these measurements. The near-infrared camera, EINER-CAM, and near-infrared spectrograph, ENIRS-PEC, could measure the continuum and absorption lines with high precision. These instruments were ideal for observing older stars, whose peak emission occurs in infrared wavelengths. The mid-infrared instrument, MIRI, was also capable of detecting warm dust or molecular gas. But in this galaxy, no significant emission was expected. Observations were planned to cover multiple wavelengths in the infrared to detect subtle variations in the light profile. Smoothness across these bands was expected, with no localized increases in brightness or emission. Spectroscopic data were expected to match predictions from stellar population synthesis models for quiescent galaxies. Molecular gas transitions, such as those from CO or H2, were expected to be below the detection limit, consistent with previous non-detections in optical and submillimeter surveys. JWST observations were also intended to verify the age estimates of stellar populations. Previous studies suggested that the galaxy's stars formed several billion years earlier, and that no significant new stars had appeared since. Infrared spectra were expected to show absorption lines dominated by low-mass, long-lived stars, confirming these age estimates. The galaxy was expected to show no ultraviolet excess, no emission line activity, and no evidence for recent star formation. The observation program assumed that quiescent galaxies like this one are stable and inactive. JWST's role was to provide more precise measurements, not to challenge this assumption. Observing the galaxy in infrared allowed astronomers to bypass dust obscuration, confirm the smooth stellar distribution, and verify the lack of gas. The expectation was that the telescope would produce data entirely consistent with the standard model of galaxy death: a smooth continuum, old stellar spectra, and no molecular gas. Why JWST changes everything. The James Webb Space Telescope is not just a bigger telescope than Hubble. It is fundamentally different in the way it sees the universe. The key to its revolutionary power lies in its infrared sensitivity, its resolution at high redshift, and its ability to see through dust that hides crucial information in galaxies. These capabilities allow astronomers to study quiescent galaxies, long considered inactive and unchanging, in a completely new way. Hubble transformed our understanding of galaxies in the optical and near-infrared. It revealed detailed structures, clumps, spiral arms, and star-forming regions in nearby and distant galaxies. However, Hubble's sensitivity drops in the infrared, especially beyond 1.6 microns. At high redshifts, where light from distant galaxies is stretched into longer wavelengths by the expansion of the universe, Hubble's instruments could see only part of the spectrum. This limitation made it difficult to study old stars, faint gas, and dust-obscured regions. JWST, designed to operate primarily in the infrared, overcomes these limits. Infrared sensitivity is the first major advantage of JWST. Older stars emit most of their light in the infrared. In quiescent galaxies, young blue stars are rare, and the remaining stellar population is dominated by cooler stars whose light peaks at red and infrared wavelengths. Hubble could detect these stars, but only partially and with limited precision. JWST's instruments, including NIRCam, are optimized to capture this infrared light with extremely high sensitivity. This allows astronomers to measure the stellar continuum of quiescent galaxies in unprecedented detail, separating contributions from stars of different ages and identifying subtle variations that were invisible to previous telescopes. The second advantage is resolution at high redshift. As galaxies become more distant, their apparent size on the sky shrinks. Hubble could resolve distant galaxies to some extent, but at redshifts above 2 or 3, many galaxies appear as barely resolved blobs. JWST's mirror, with its 6.5-meter diameter and advanced optical design, provides sharper images at longer wavelengths than Hubble could achieve in the optical. This higher resolution allows astronomers to distinguish structures within distant galaxies, including faint clumps of stars, potential gas pockets, and small irregularities in otherwise smooth elliptical galaxies. For quiescent galaxies, which were assumed to be featureless, this capability is transformative. It reveals details that challenge previous classifications. The third advantage is dust penetration. Galaxies contain dust that absorbs optical and ultraviolet light, re-emitting it in the infrared. In quiescent galaxies, this dust is often cold and faint, making it difficult to detect with Hubble or ground-based telescopes. Dust can obscure residual star formation, molecular gas, or faint emission lines that would reveal ongoing activity. JWST operates in the infrared, allowing it to see through dust and detect light from stars and gas that was previously hidden. This makes it possible to test whether quiescent galaxies are truly inactive or if they contain faint, obscured activity. JWST's power comes from its key instruments, which work together to provide a comprehensive view of galaxies. NIR-CAM, the near-infrared camera, captures high-resolution images in multiple infrared bands. It is used to map the distribution of stars, detect subtle structures, and measure the continuum light from old stellar populations. NIR-SPEC, the near-infrared spectrograph, collects spectra that reveal stellar ages, metallicities, and gas content. It can detect faint emission and absorption lines even in galaxies thought to be inactive. MIRI, the mid-infrared instrument, extends the coverage to longer wavelengths, allowing astronomers to detect warm dust, molecular gas, and emission from obscured regions. Together, these instruments provide a full picture of a galaxy's composition and structure in infrared light. Infrared observations matter particularly for quiescent galaxies. In optical light, these galaxies appear red and featureless. Their smooth elliptical shapes suggest inactivity, and weak emission lines indicate little or no star formation. But optical observations are limited by dust obscuration and the decreasing contribution of older stars at shorter wavelengths. Infrared light penetrates dust and provides a more direct view of the stellar population. It can reveal faint clumps of young stars, residual gas reservoirs, or subtle structural features that were invisible before. JWST's infrared view allows astronomers to test whether quiescent galaxies are truly dead or only appear so in the optical. The infrared continuum measured by JWST is critical for identifying different generations of stars. Old stars emit steadily in the near-infrared, while young stars contribute less at these wavelengths but dominate in the ultraviolet and optical. By analysing the continuum across multiple infrared bands, astronomers can determine the fraction of old versus young stars, constrain stellar ages, and detect low-level star formation. For galaxies classified as quiescent, this means confirming the dominance of old stars or identifying previously unseen younger populations. Spectroscopy with NIR-SPEC adds another layer of detail. Absorption lines in the spectra reveal chemical abundances and stellar ages. For quiescent galaxies, strong absorption features from magnesium, iron, and other metals indicate past star formation histories. Weak or absent emission lines indicate little gas activity. JWST can measure these lines with higher precision than Hubble, revealing even faint signals that might indicate residual gas or recent star formation. This capability directly tests the standard model of galaxy death. MIRI extends these measurements to longer wavelengths, detecting warm dust and molecular gas. Even a small amount of molecular gas can produce emission lines in the mid-infrared. Quiescent galaxies were assumed to lack these features, but JWST can detect gas that is cold, faint, or hidden behind dust. This provides direct evidence about the presence or absence of star-forming material, which is critical for understanding whether a galaxy is truly inactive or only partially quenched. JWST's combination of infrared sensitivity, high-resolution imaging, and spectroscopic capabilities transforms the study of quiescent galaxies. Previously, these galaxies were classified as dead based on optical data that missed faint activity, dust-obscured regions, and older stellar populations. With JWST, astronomers can detect features that were invisible before: residual star formation, molecular gas, subtle clumps, and complex stellar populations. Every aspect of the galaxy's structure and composition can now be measured with precision. This capability changes the expectations for what quiescent galaxies are. Optical observations suggested smooth, uniform light, dominated by old stars, with no significant gas or star formation. Infrared observations revealed that some of these galaxies may harbour faint activity, small gas reservoirs, or young stars that were previously undetectable. Even galaxies classified as fully dead may contain features that indicate ongoing evolution. JWST allows scientists to quantify these contributions and understand the full range of galaxy properties. Infrared imaging also provides spatial context. NIR-CAM images allow astronomers to map where stars, gas, and dust are located within the galaxy. This reveals whether any residual activity is spread evenly or concentrated in small regions. Such mapping was impossible with Hubble at high redshift, where resolution limitations made distant galaxies appear featureless. JWST's resolution and sensitivity allow detailed spatial studies of galaxies billions of light-years away. Finally, JWST observations can directly test theoretical models. Simulations of galaxy formation predict when and how galaxies stop forming stars, how gas is depleted or expelled, and how stellar populations evolve over time. By observing galaxies in the infrared, JWST can measure the actual stellar ages, gas content, and structure, and compare these measurements with predictions. Any discrepancies can refine models, improve understanding of galaxy evolution, and challenge assumptions based on optical data alone. Infrared observations are also critical for understanding the role of dust. In quiescent galaxies, small amounts of dust can obscure star formation or molecular gas. Optical observations may interpret the lack of blue light as a sign of inactivity, when in fact dust is absorbing it. JWST's ability to see through dust removes this ambiguity. It allows astronomers to distinguish between truly dead galaxies and those that only appear dead because their activity is hidden. The observation setup. When scientists decided to point JWST at this galaxy, everything was carefully planned. The galaxy is very far away, which means we are seeing it as it was billions of years ago, in the early universe. Its light is stretched out because of the universe's expansion, which astronomers call redshift. This galaxy has a redshift that places it in a time when the universe was only a few billion years old. Studying galaxies at this stage is tricky because their light is faint and most of it has shifted into the infrared. That's why JWST was needed. Hubble could see the galaxy in visible light, but it barely detected anything. JWST can see it clearly in infrared, where most of its light arrives. Planning the observation meant calculating how long the telescope needed to stare at the galaxy. Exposure time is critical. If the exposure is too short, the light is too faint, and the images are noisy. If it's long enough, JWST can capture details of the galaxy's stars, gas, and dust. For this galaxy, astronomers set long exposure times, taking hours to collect enough photons for a clear picture. The telescope needed to gather enough light to measure the faint infrared continuum, detect subtle absorption lines in the stars, and look for any molecular gas that might remain. The observation had two main goals: imaging and spectroscopy. Imaging is what most people think of when they picture a telescope. NIR-CAM took pictures across multiple infrared bands, mapping how light is distributed in the galaxy. Scientists wanted to see whether the galaxy was smooth, as expected for a quiescent system, or if there were any hidden clumps of stars. Imaging also allows astronomers to see faint structures that were invisible to Hubble, like small star-forming regions or leftover dust lanes. Spectroscopy was the other key goal. NIRSpec collects light and spreads it into a spectrum, like a rainbow. This reveals chemical fingerprints, absorption lines from stars, and emission lines from gas. Scientists were looking for evidence of old stars, their ages, and their chemical makeup. They also checked for molecular gas lines, which would indicate leftover fuel for star formation. Spectroscopy can tell you if a galaxy that looks dead is truly dead or just hiding a little activity. For this galaxy, spectroscopic data was crucial because previous optical studies could only suggest that it was quiescent. JWST could test that directly. Before the observation, scientists had a clear expectation. They assumed the galaxy would show a smooth infrared continuum, meaning light would be evenly distributed across the galaxy. They expected absorption lines from old stars and no detectable molecular gas. The observation was designed to confirm this. No one expected to find anything new. The telescope setup, the choice of filters, and the exposure times were all optimized for precision, not discovery. JWST's instruments were chosen carefully. NIR-CAM would take high-resolution images in multiple bands, each capturing slightly different wavelengths of infrared light. This allows scientists to separate contributions from stars of different ages and detect faint structures. NIR-spec would record the spectra to measure ages, metallicities, and gas content. MIRE, operating at longer wavelengths, could detect warm dust or faint molecular gas. The combination of these instruments was designed to provide a complete view of the galaxy in the infrared. The redshift of the galaxy influenced the setup in several ways. Because the galaxy is so distant, its light is redshifted into longer wavelengths. Features that would appear in the optical for nearby galaxies are shifted into the infrared for this one. The observation plan had to account for that. Filters were selected to match the redshifted wavelengths of key stellar and gas features. Spectroscopic settings were adjusted to capture absorption lines from old stars at these wavelengths. Every detail was calculated to make sure JWST could see what was expected. Exposure times were longer than typical because quiescent galaxies are faint. Unlike starburst galaxies, which shine brightly in ultraviolet and visible light, this galaxy emits mostly in the infrared, from older, cooler stars. Collecting enough photons to get clean spectra and detailed images required hours of integration. The telescope's stability and cooling system allowed it to stay focused for these long periods without interference from thermal noise or vibrations. Imaging and spectroscopy work together. Images help place the spectra in context. If spectroscopy detects absorption lines, scientists need to know exactly where in the galaxy they came from. NIR-CAM maps the light, showing the structure, while NIR-spec measures the composition. For quiescent galaxies, this combination is essential. A smooth image with old star spectra confirms inactivity. Any deviations, like clumps or gas emission, would indicate unexpected activity. During planning, astronomers also considered background noise. The early universe is filled with faint infrared light from other sources. JWST had to distinguish the galaxy's light from this background. Careful positioning and multiple exposures reduced contamination. Scientists also included reference stars and blank sky measurements to calibrate the data and correct for any instrumental effects. Every step was designed to ensure the observation would provide accurate confirmation of the galaxy's quiescent state. The data scientists were looking for were specific. First, They wanted a smooth continuum in the infrared, consistent with a population of old stars. They wanted strong absorption lines from red giants and low-mass stars, with no emission lines from active star formation. They wanted to detect, or definitively rule out, molecular gas. They also examined the galaxy for any small irregularities, faint dust, or subtle clumps that could indicate residual activity. Every measurement was planned to test the standard model of galaxy death directly. JWST's imaging resolution at high redshift meant that even small structures could be resolved. At this distance, a galaxy appears tiny on the sky. Hubble could only show it as a small blob. JWST could measure light profiles in detail, detect variations in brightness across the galaxy, and map the distribution of stars precisely. For quiescent galaxies, this is crucial. Small clumps of stars or leftover gas could be missed by less sensitive telescopes. JWST's high resolution ensured that nothing would be overlooked. Spectroscopy had similar advantages. High-resolution spectra allow scientists to measure stellar ages to high precision. They can detect weak absorption lines and subtle features that reveal the chemical history of the galaxy. They can also search for weak molecular lines that indicate remaining gas. For this galaxy, the spectroscopic setup was optimized to capture everything from the continuum to faint lines, leaving no possibility of missing hidden activity. The observation plan also considered time variability. Quiescent galaxies are assumed to be stable, but JWST's repeated exposures over hours could reveal small fluctuations in emission that indicate low-level activity. These measurements were included as part of the observation strategy. Even though no major changes were expected, the telescope was capable of detecting surprises if they existed. Calibration was part of the setup too. Scientists used nearby reference stars and blank sky fields to correct for instrumental noise and atmospheric interference, even though JWST is in space. These calibrations ensured that the faint signals from the galaxy could be measured accurately. Long exposure times combined with careful calibration provided high signal-to-noise data, necessary for studying galaxies that appear inactive. The observation also used multiple filters and spectral settings. Each filter targets a specific wavelength range. This allows astronomers to measure contributions from different types of stars and detect possible gas or dust emission. Spectral settings were chosen to cover key absorption and emission lines relevant to quiescent galaxies. JWST's flexibility allowed scientists to design a setup that maximized the chance of confirming expectations while still being sensitive enough to detect faint, unexpected features. JWST's stability, cooling system, and sensitive detectors were all essential for the setup. Long exposures in the infrared require extremely low background noise. Thermal emission from the telescope itself can interfere with measurements, so JWST's sunshield and cryogenic instruments reduce noise to minimal levels. This allows the telescope to measure faint light from old stars billions of light-years away, with clarity impossible from the ground or with previous space telescopes. The setup also accounted for the redshifted molecular lines. Even if the galaxy were truly dead, astronomers wanted to rule out any small reservoirs of gas. JWST's instruments could detect faint emission lines from molecules like CO and H2 at these redshifted wavelengths. Selecting the correct spectral windows ensured that if any gas existed, it would be detected. The unexpected light. The first images and spectra from JWST arrived, and scientists immediately noticed something strange. The galaxy, which had been labelled as dead for decades, was emitting infrared light where none was expected. The instruments detected more emission than predicted from the old stars alone. The light wasn't just faint background noise, it was measurable, structured, and inconsistent with the smooth continuum that astronomers had expected. The detection itself was precise. NIRCam images showed brightness across several infrared bands, and NIRSpec spectra confirmed absorption and emission lines in places that should have been silent. MIRI data hinted at warm dust or faint molecular gas in regions of the galaxy that optical studies had considered empty. Every instrument showed the same unexpected signal. The galaxy wasn't as quiescent as previously thought. What made this immediately suspicious was the spatial distribution of the light. Instead of being smooth and uniform, as expected for a quiescent elliptical galaxy, the infrared emission showed subtle variations across the galaxy's shape. Some areas were slightly brighter than others, forming small clumps of light. These clumps were faint but distinct, enough to stand out against the uniform glow from older stars. The distribution wasn't random either. It appeared structured, with brighter patches concentrated in specific regions rather than evenly spread. Scientists compared these patterns to expectations. In a truly quiescent galaxy, the infrared light from old stars should create a smooth profile, gradually fading from the center to the edges. Minor variations are normal due to differences in star density, but nothing on the scale detected by JWST had been predicted. The presence of small, localized bright spots suggested that something else was producing light in these regions. Spectroscopy reinforced the suspicion. While absorption lines from old stars dominated the spectra, faint emission lines appeared in the same regions as the bright clumps. These lines indicated the presence of gas at temperatures and densities inconsistent with a purely passive galaxy. The wavelengths match molecular transitions and ionized gas features that should not have been visible if the galaxy were fully dead. Scientists realized that these signals could not be explained by instrumental noise or background contamination. They were real and localized within the galaxy itself. The pattern of light was also unexpected in terms of scale. Some clumps were small, barely a fraction of the galaxy's total size, while others extended across hundreds or thousands of light years. This suggested that the process producing the emission was neither uniform nor confined to a single region. In other words, there was activity in the galaxy that optical telescopes had completely missed. Even Hubble's deep images showed no hint of these structures because the light was shifted into the infrared. JWST had opened a new window onto the galaxy, revealing features that were invisible before. The brightness of the unexpected light varied across bands. Shorter wavelength infrared images were dominated by the old stellar continuum, as expected, but longer wavelengths revealed the clumps more clearly. This indicated that the source of the light was not purely from old stars. Some of the emission could be associated with residual star formation, where young stars are forming in small pockets. Other components could be from warm dust or molecular gas heated by past star formation or low-level activity. The combination of sources explained why the galaxy appeared brighter in certain infrared bands than models had predicted. The irregular distribution was immediately suspicious because it contradicted decades of assumptions. Astronomers had classified the galaxy as quiescent based on smooth optical light, weak emission lines, and the absence of dust lanes. JWST showed that this classification was oversimplified. The galaxy contained regions that were producing light in ways that standard models of galaxy death could not account for. The very presence of these clumps challenged the idea that the galaxy had stopped evolving billions of years ago. Scientists also compared the observed light to theoretical predictions. Models of quiescent galaxies assume a smooth decline in star formation, leading to uniform infrared emission from older stars. Some small variations are expected due to random distribution of stars or minor mergers. But JWST revealed patterns that were stronger and more structured than predicted. The bright spots were not just statistical fluctuations. they were significant, measurable deviations from the expected light profile. This made it clear that something new was happening. Another reason the light was suspicious was its location within the galaxy. The clumps were not confined to the centre, where an old supermassive black hole might dominate energy output. They were scattered across the disk and outer regions. This suggested that the emission was not the result of a single active nucleus, but likely came from distributed sources. Possible explanations included faint star-forming regions, leftover molecular clouds, or localized heating of dust. Each of these possibilities indicated that the galaxy retained some form of activity. The emission lines detected by NIR spec added another layer of mystery. Lines associated with molecular gas and ionized hydrogen appeared exactly where the infrared clumps were brightest. These lines are typically linked to star formation or energetic processes. In a quiescent galaxy, such emission should be absent or extremely weak. The fact that JWST detected them, spatially aligned with the clumps, suggested ongoing processes that had been entirely invisible to previous surveys. JWST's ability to detect faint infrared signals was crucial in revealing these features. Ground-based telescopes and Hubble simply did not have the combination of sensitivity and resolution required. Even if small pockets of star formation existed, they would have been overwhelmed by the older stellar population in optical observations. JWST's instruments separated these components, allowing scientists to see faint activity alongside the dominant old stars. The structure of the light also hinted at the galaxy's history. Bright clumps scattered across the galaxy could be remnants of small mergers or accretions. They might also represent localized pockets of gas that survived earlier quenching processes. Either way, the pattern contradicted the idea of a completely passive galaxy. JWST revealed that quiescent galaxies are more complex than previously thought, with hidden structures that optical surveys could not resolve. Scientists ran multiple checks to ensure the signal was real. They compared different filters, instruments, and exposure times. The clumps appeared consistently across all observations. They ruled out cosmic rays, detector noise, and background contamination. The light was genuinely coming from the galaxy itself, and its distribution was clearly irregular. This was not a minor anomaly. It was a direct observation that something unexpected was happening in a galaxy classified as dead. The clump's brightness, while faint compared to the total light of the galaxy, was significant in relative terms. Models predicted less than 1% of emission in these regions, but JWST measured several times more than expected. This indicated that the processes generating the light, whether faint star formation or leftover gas heating, were not trivial. They were enough to alter the galaxy's classification and challenge standard assumptions. Even more surprising was the wavelength dependence of the clumps. Shorter infrared wavelengths showed only subtle hints, consistent with older stars, while longer wavelengths highlighted the clumps strongly. This indicated that the emission was coming from cooler sources, like molecular gas heated by star formation or dust warmed by energetic processes. The difference across bands made it clear that JWST was seeing components completely invisible in previous optical surveys. The combination of brightness, spatial distribution, and wavelength dependence made the observation immediately suspicious. A smooth, quiescent galaxy should not display these features. The galaxy was not just slightly active, it had measurable, structured emission in multiple infrared bands distributed across its shape. This suggested that the processes behind galaxy quenching are more complicated than previously thought, and that even galaxies classified as dead can retain hidden activity for billions of years. Every scientist in the team understood the significance immediately. The unexpected light meant that quiescent galaxies are not entirely inert. Hidden pockets of gas, faint star formation, or residual dust could persist far longer than models predicted. The data from JWST opened a new window into galaxy evolution, revealing activity that optical telescopes could never detect. The smooth, red, featureless galaxies that had been assumed dead for decades were now revealed to be more dynamic and complex. The discovery also raised new questions. Were these clumps remnants of the galaxy's past, slowly fading away? Were they evidence of faint, ongoing star formation? Could they indicate that the quenching process is not as complete as previously assumed? JWST had provided the first direct observations that challenged the assumption of uniform inactivity, and the unexpected light demanded a re-evaluation of how galaxies die. JWST's instruments continued to provide consistent results across the galaxy. NIR CAM imaging, NIR SPEC spectroscopy, and MIRI measurements all detected faint emission where none was expected. The clumps appeared in the same locations across multiple exposures, confirming that this was not a random artifact. The spatial distribution of the light, the spectral signatures, and the wavelength-dependent brightness all pointed to a real, measurable phenomenon. Emission lines where none should be. The moment astronomers examined the spectra from JWST, they noticed something that did not fit any of their expectations. In a galaxy labelled as quiescent, as in completely dead, certain emission lines appeared clearly, even though the galaxy was supposed to be devoid of gas and active star formation. These lines were not subtle hints. They were measurable, distinct signals standing out against the smooth continuum from old stars. One of the first features scientists identified were hydrogen recombination lines. These lines occur when hydrogen atoms have their electrons knocked away and then recapture them, releasing energy as light at very specific wavelengths. In active galaxies, these lines are common because new stars produce intense ultraviolet radiation that ionizes hydrogen in surrounding gas clouds. The recombination of electrons produces the familiar H-alpha and H-beta emission lines. In a quiescent galaxy, where star formation has supposedly stopped billions of years earlier, no such ionizing radiation should exist. Hydrogen should mostly be neutral, cold, and invisible in the spectrum. Yet JWST detected these recombination lines clearly in several regions of the galaxy. Alongside hydrogen, astronomers observed lines from ionized oxygen and neon. These elements require even more energy to ionize than hydrogen. For oxygen to emit in the observed lines, photons with energies capable of stripping multiple electrons from oxygen atoms are necessary. Neon requires similarly high energy radiation. In star-forming galaxies, these ionized lines appear because massive young stars emit intense ultraviolet light, creating ionized regions known as H2 regions. In this galaxy, which was expected to contain only old low-mass stars, these lines should have been absent. The fact that JWST detected them in the spectra immediately raised questions. The physical meaning of these emission lines is significant. They indicate that gas is being ionized, energized by photons or processes strong enough to strip electrons from atoms. Hydrogen recombination lines suggest that the galaxy contains pockets of gas being ionized and then recombining, meaning that some form of energy source is actively influencing the gas. Ionized oxygen and neon lines indicate even higher energy processes. The gas is not passive. It is being affected by radiation, heating, or shocks. This is fundamentally inconsistent with the standard model of quiescent galaxies, where stars are old and gas reservoirs are depleted or expelled. Old stars alone cannot produce these emission lines. Red giants, low-mass main-sequence stars, and other remnants of the old stellar population emit primarily in red and infrared light. They lack the ultraviolet radiation needed to ionize hydrogen or heavier elements. There are some exceptions, like planetary nebulae and evolved stellar remnants. But the scale of the emission detected by JWST far exceeded what could be explained by these minor sources. The emission lines were too widespread, too strong, and too structured to be caused by old stars alone. The hydrogen recombination lines alone were enough to spark excitement. AH alpha and H beta lines are direct indicators of ionized gas. In normal quiescent galaxies, these lines are weak or absent because the gas is cold or has been blown out by supernovae or active galactic nuclei. Here, JWST revealed clear recombination lines across multiple regions of the galaxy, suggesting that hydrogen gas is present and interacting with some energy source. The light from old stars cannot provide enough ionizing photons to create these features. The oxygen and neon lines added to the puzzle. Emission from doubly ionized oxygen, O3, or neon, Ne3, requires photons with energies above 35 electron volts for oxygen and over 40 electron volts for neon. These energies are typically produced by young, massive stars or extreme sources like active galactic nuclei. Old stars cannot generate such high-energy radiation. Therefore, the presence of these lines implied that the galaxy contained processes capable of ionizing elements far heavier than hydrogen, suggesting either faint star formation or an unexpected energy source. JWST's ability to spatially resolve these emission lines made the discovery even more striking. The emission was not uniform. It appeared in localized clumps and patches, aligned with the regions where the unexpected infrared light was brightest. This distribution indicated that whatever was producing the ionization was concentrated in specific areas of the galaxy, not evenly spread throughout. Old stars alone, distributed smoothly across the galaxy, would produce a uniform light profile, not the structured emission detected. Spectroscopic analysis confirmed the line ratios. Scientists compared the intensities of hydrogen, oxygen, and neon lines. The ratios matched those seen in low-level star formation or weakly active regions, but they did not match what would be expected from old stars. The data showed that the ionized gas was similar in properties to regions in star-forming galaxies, just much fainter. This provided further evidence that the galaxy was not entirely dead, as previously believed. JWST's sensitivity and resolution were key to detecting these lines. Previous telescopes, including Hubble, lacked the infrared coverage and precision to detect faint emission lines at the galaxy's high redshift. Even if gas had existed, its light would have been redshifted into wavelengths invisible to older instruments. JWST's instruments, NIR spec for spectroscopy and MIRI for longer wavelengths, captured the lines with clarity, separating them from the continuum and resolving their spatial distribution. This combination made it possible to detect emission lines that had been hiding in plain sight for decades. The discovery forced a re-evaluation of what quiescent means. For decades, astronomers classified galaxies as quiescent based on smooth optical light, lack of obvious emission lines, and absence of dust lanes. The emission lines detected by JWST showed that even galaxies classified as dead can retain ionized gas, pockets of energy, and potential star-forming material. This suggests that galaxy quenching may not be complete, or at least not uniform, across the galaxy. Scientists also explored possible sources for the ionization. Faint, low-level star formation is one candidate. Even a small number of young, massive stars can produce sufficient ultraviolet light to ionize hydrogen and some oxygen. Another possibility is weak activity from a central supermassive black hole, known as a low-luminosity active galactic nucleus. Such a black hole could produce high-energy photons capable of ionizing oxygen and neon. Shock heating, caused by gas dynamics or minor mergers, is another plausible explanation. Each of these mechanisms could account for the observed emission lines, but none had been expected in a galaxy previously classified as fully quiescent. The combination of hydrogen, oxygen and neon lines is especially informative. Hydrogen lines indicate the presence of gas that is recombining, while oxygen and neon lines indicate higher energy ionization. Together, they suggest a multi-phase interstellar medium. Some gas is cooler and slowly recombining, while some gas is hotter or more energetic, possibly heated by radiation or shocks. Old stars, producing only low-energy light, cannot create this multi-phase ionization. JWST revealed that the galaxy contains complex, structured gas dynamics, despite its classification as dead. JWST's spectral resolution allowed scientists to measure the velocity of the ionized gas. The emission lines were not perfectly at rest. Some were slightly shifted due to motion within the galaxy. This provided evidence that the gas was not static but moving, potentially influenced by local star formation, shocks, or weak AGN activity. Again, old stars alone could not produce moving, ionized gas on this scale. The presence of velocity shifts confirmed that the galaxy retained active physical processes. The distribution of emission lines also correlated with the infrared clumps seen in imaging. This connection was crucial because it showed that the unexpected light and the ionized gas came from the same regions. The brightest infrared clumps coincided with stronger hydrogen and oxygen emission, suggesting that these areas are still evolving in some way. This spatial correlation makes it clear that JWST was seeing physical activity that optical studies had missed, rather than random noise or artifacts. Even the faintest lines were significant. Previous optical surveys would have classified any galaxy with emission line strengths below detection limits as quiescent. JWST's sensitivity exposed these faint lines, revealing that quiescent galaxies are not uniform in their inactivity. Small residual activity can persist in isolated clumps, and it is visible only with the combination of infrared sensitivity, high resolution, and spectroscopic precision that JWST provides. The presence of emission lines also changes how astronomers think about galaxy evolution. Quenching is not a simple on-off process. The galaxy may have stopped forming stars on a large scale, but pockets of activity remain. Hydrogen recombination lines and ionized oxygen and neon lines show that energy and gas dynamics are still present. Old stars alone cannot explain these features. JWST has revealed that quiescent galaxies are more dynamic, more structured, and more active than previously assumed. Molecular gas discovery. JWST's observations didn't just show unexpected light or emission lines. The telescope revealed cold molecular gas in a galaxy that had been classified as dead for decades. Molecular gas is composed mainly of hydrogen molecules, H2, sometimes traced with carbon monoxide, CO, or other molecules, and it's the raw fuel for star formation. In theory, quiescent galaxies should have exhausted or expelled nearly all of this gas, leaving nothing for new stars to form. Using MIRI and NearSpec, astronomers detected faint signals of cold molecular gas. These detections weren't obvious in the initial images. They appeared only after careful spectral analysis. The lines corresponded to rotational transitions of molecules in the infrared, shifted to longer wavelengths by the galaxy's high redshift. Even though the signals were weak compared to starburst galaxies, they were measurable, structured, and extended across the galaxy. The presence of molecular gas in a quiescent galaxy immediately raised questions, because molecular gas is the fuel for star formation. If a galaxy still contains molecular gas, it has the raw ingredients to form new stars. The standard model of galaxy death assumes that once a galaxy stops forming stars, its gas is either consumed, expelled by supernova, or AGN activity, or heated so that it cannot collapse into stars. Detecting cold molecular gas means that the galaxy has the potential to form stars again, which contradicts its classification as dead. The scale of the detection was significant. JWST revealed gas reservoirs that were small compared to the galaxy's total mass, but large compared to the levels expected for quiescent galaxies. Astronomers measured gas masses of several percent of the stellar mass in the galaxy. In numbers, for a galaxy with a stellar mass of 10 to the power of 11 solar masses, the molecular gas mass was on the order of 10 to the power of 9 solar masses. This is not enough to reignite full-scale star formation immediately, but it is far above the negligible amounts predicted by models for dead galaxies. The gas was not concentrated in the centre. JWST's resolution allowed astronomers to map the molecular gas spatially, revealing patchy clumps distributed across the galaxy. Some clumps coincided with the previously detected infrared light and emission line regions. Others appeared in more isolated parts of the galaxy. The distribution suggested that the gas had survived past quenching events, possibly shielded in pockets where star formation had ceased or slowed, but not completely stopped. JWST's spectral analysis of the molecular gas also revealed its temperature and density. The gas was cold, on the order of tens of Kelvin, meaning it could collapse under gravity to form stars if triggered. The density was low compared to active star-forming clouds, but high enough that localized star formation could occur. The physical properties of the gas were consistent with a fossil reservoir, gas that had survived earlier energetic events and remained capable of forming stars, but in a highly inefficient or intermittent manner. The detection of molecular gas directly contradicted previous assumptions. Surveys with Hubble and ground-based telescopes had concluded that the galaxy was depleted of gas. Optical spectroscopy and previous infrared observations were consistent with this conclusion, showing no detectable emission lines or dust signatures. JWST, with its higher sensitivity in the infrared, revealed the gas that had been hidden from view. This demonstrated that molecular gas can persist in galaxies even after star formation has largely stopped. The mass of the molecular gas was small enough that the galaxy still appears quiescent overall, but large enough to produce measurable emission lines. This explains why JWST detected hydrogen recombination lines and ionized oxygen in the same regions. The gas is dense enough to interact with radiation, producing emission lines, but not dense or abundant enough to create a full starburst. The coexistence of cold molecular gas and low-level emission lines is a new phenomenon for galaxies previously classified as dead. The presence of gas also implied that galaxy quenching is not absolute. Star formation may be suppressed by heating, turbulence, or AGN feedback, but it is not completely impossible. Pockets of molecular gas can survive for billions of years, remaining dormant until conditions allow them to collapse and form stars. JWST's detection showed that quiescent galaxies are not uniform, empty shells, but can retain molecular material in hidden regions. JWST's imaging and spectroscopy together confirmed that the gas is physically associated with the galaxy. The spectral lines appeared at the same redshift as the galaxy, ruling out contamination from foreground or background objects. The emission was extended over the same regions where the infrared light and emission lines were strongest, confirming that the gas is located within the galaxy, not in a companion or unrelated structure. The molecular gas was also cooler than expected. In active star-forming galaxies, gas is often heated by young stars or shocks to hundreds or thousands of Kelvin. In this quiescent galaxy, the gas was cold enough to be considered stable, yet still capable of forming stars. The combination of cold temperature, measurable density, and spatial structure made it a unique finding. The galaxy retained star-forming fuel, but in a dormant state. The discovery challenged the understanding of galaxy life cycles. Previously, galaxies were thought to exhaust or lose their gas during a quenching phase, transitioning into a long passive period with little to no potential for new star formation. The presence of molecular gas in a quiescent galaxy indicates that gas depletion is not always complete, and galaxies can retain reservoirs of star-forming material even after billions of years of inactivity. The quantity of gas also has implications for star formation efficiency. If the molecular gas were triggered, it could form stars at a slow, steady rate, producing low-level activity over long timescales. The observed gas mass was enough to support these faint star formation rates, which could explain the emission lines and clumpy infrared light detected by JWST. Old stars alone could not account for these signals. The molecular gas provides a direct source for ongoing activity. Mapping the gas with JWST revealed patterns in the galaxy's structure. Gas clumps were often located near regions of previous star formation or areas where residual dust was detected. This suggests that some of the molecular gas survived the initial quenching events because it was shielded from energetic feedback, such as supernova explosions or AGN activity. The survival of these pockets indicates that galaxy death is not a single event, but a process that can leave behind remnants capable of slow regeneration. Even small quantities of molecular gas are enough to maintain detectable emission lines. Hydrogen recombination lines and ionized oxygen can arise from interactions with only a fraction of the total gas present. JWST's sensitivity allowed scientists to measure these faint signals and connect them to the molecular gas reservoirs. The combined evidence from infrared imaging, emission lines, and molecular gas maps painted a picture of a galaxy that is far more complex than previously thought. The spatial resolution of JWST also allowed scientists to measure the velocity dispersion of the molecular gas. Some clumps showed slight motion relative to the galaxy's center, indicating that the gas is not completely static. This movement could be the result of turbulence, weak gravitational interactions, or residual rotation from the galaxy's formation. Even though the galaxy is classified as dead in terms of star formation, the gas is physically active, moving, and capable of producing emission. The total mass of molecular gas, while small relative to the galaxy's total stellar mass, is large enough to challenge standard models. Quiescent galaxies were assumed to be almost completely devoid of molecular gas, but JWST measured several billion solar masses of cold gas in this galaxy. This amount is sufficient to sustain faint star formation, ionize the gas to produce emission lines, and create the clumpy infrared light detected in imaging. Where the gas is hiding. JWST didn't just detect molecular gas in the galaxy, it also revealed exactly where it is hiding. The telescope's unprecedented spatial resolution allowed astronomers to map the gas in detail for the first time. Instead of being spread evenly across the galaxy, the cold molecular gas appeared in clumps, patches, and localized regions, sometimes associated with faint infrared light and emission lines. The gas wasn't forming a uniform disk like in active spiral galaxies. It wasn't distributed smoothly like old stars. It was hiding in specific pockets, invisible to previous instruments. NERSpec and MIRI both contributed to this mapping. NERSpec provided detailed spectra across multiple positions, revealing where molecular emission lines were strongest. MIRI added longer wavelength imaging, sensitive to cooler gas and dust. Combining the data created a three-dimensional picture. The galaxy is full of small, isolated gas clumps, each spanning hundreds to thousands of light years. These clumps were scattered throughout the galaxy, rather than concentrated in the center or along a spiral structure. Some of the clumps coincided with regions of unexpected infrared light. NIR-CAM images showed slightly brighter spots where old stars alone could not account for the luminosity. JWST's spectroscopic mapping confirmed that these regions contain molecular gas and faint emission lines, including hydrogen recombination and ionized oxygen. The clumps were sites where the galaxy retained star-forming fuel, even though most of the galaxy appeared inactive. Other clumps were located in isolated areas of the galaxy, with no obvious association to visible stellar structures. These pockets may have survived past energetic events, like supernova-driven winds or weak AGN feedback, which expelled or heated most of the gas in the galaxy. The survival of these clumps suggests that gas removal in quiescent galaxies is not perfectly efficient. Even billions of years after the main star formation period ended, small reservoirs can persist in protected regions. The distribution of molecular gas was irregular. JWST maps showed that some clumps were elongated, suggesting gas streams or filamentary structures. Others were roughly spherical, appearing as compact clouds. The variety of shapes indicates that the internal dynamics of the gas are complex. Some clumps may be remnants of small mergers or accretions, while others may have condensed from leftover gas within the galaxy. This patchiness is a pattern that previous telescopes could not detect. JWST also revealed evidence of internal structure within the clumps themselves. Spectra showed variations in gas density and temperature across individual clouds. Some clumps contained denser cores capable of collapsing into stars if conditions allow, while outer layers were more diffuse. The combination of dense cores and diffuse envelopes suggests that the gas is in a transitional state, neither fully forming stars nor completely inert. This structure had been theorized in simulations, but never directly observed in a high redshift quiescent galaxy before JWST. Mapping also revealed small velocity differences among clumps. Some molecular clouds were moving slightly faster or slower relative to the galaxy's center. These velocity shifts indicate that the gas is not static. It may be rotating, slowly collapsing, or experiencing mild turbulence. JWST's spatially resolved spectroscopy allowed scientists to measure these motions for the first time, giving insight into the physical state of gas in a galaxy long considered dead. When comparing these observations with cosmological simulations, astronomers found interesting matches and discrepancies. Simulations of quiescent galaxies predicted that small gas reservoirs could survive in pockets, shielded from feedback processes. These pockets were expected to be clumpy and low in mass, similar to what JWST revealed. However, simulations often assume simpler distributions and lower densities. The real galaxy's clumps were sometimes denser, more extended and more structured than models predicted, indicating that quenching processes are more complex in practice. The gas distribution also showed clumps outside the central regions of the galaxy. In many models, quenching is most efficient in the core, where supermassive black holes and dense stellar populations generate strong feedback. Outer regions are expected to retain gas for longer periods. JWST confirmed this pattern in part, but it also detected clumps near the galaxy's center. These central clumps are small and faint, yet their presence demonstrates that gas can survive even in regions where quenching should have been most effective. JWST's mapping revealed a galaxy with multi-scale structure. On large scales, the molecular gas appears as scattered clumps, distributed across the galaxy. On smaller scales, each clump contains substructures with variations in density, temperature, and motion. The combination of these scales indicates that molecular gas in quiescent galaxies is neither uniform nor random. It retains structure, motion, and the potential for localized activity, even in galaxies classified as dead. The comparison with simulations highlighted one key point. Galaxies may remain partially active for much longer than models suggest. Simulations often treat quenching as a sharp transition, removing most gas and halting star formation. JWST's observations show that gas removal can be incomplete, leaving pockets that persist for billions of years. These reservoirs are enough to produce faint emission lines, localized infrared light, and potentially small-scale star formation, changing how scientists think about the later stages of galaxy evolution. The clumpy structure also affects the interpretation of emission lines. The hydrogen recombination and ionized oxygen lines detected earlier are strongest in the same clumps where molecular gas resides. This spatial correlation makes sense physically. The gas is being ionized locally, producing emission where it exists. Uniform distributions of old stars alone cannot generate these localized features. The mapping shows that JWST is not just detecting unexpected emission. It is pinpointing the physical origin of the activity. JWST mapping also revealed variations in clump properties with radius. Clumps closer to the galaxy's center tended to be slightly denser and warmer, while outer clumps were more diffuse and cooler. This gradient is consistent with theoretical expectations. Central regions experience stronger radiation and feedback, compressing gas slightly, while outer regions are more shielded. The observations provide the first direct confirmation of these radial trends in molecular gas within a high redshift quiescent galaxy. The internal substructure of the clump suggests that the gas may not remain static indefinitely. Dense cores could eventually collapse, forming new stars. Diffuse envelopes may slowly dissipate or merge with nearby clumps. The multi-layered structure shows that gas reservoirs are dynamic, even in galaxies thought to be dead. JWST's mapping provides a detailed view of this dynamism, revealing processes that optical studies could never detect. In addition to internal structure, JWST detected possible signs of small-scale rotation or streaming motion within some clumps. Velocity maps from NIRSPEC show slight shifts across individual clouds, suggesting internal dynamics. Some clumps appear elongated along their motion vectors, which may indicate inflow or outflow patterns. These measurements provide evidence that gas in quiescent galaxies is not simply static. It is affected by gravity, turbulence, and residual feedback processes. The discovery of clumps also explains the galaxy's previously unexpected infrared emission. The light is concentrated in the same regions where molecular gas resides. These clumps can contain dust heated by radiation, low-level star formation, or shocks, all contributing to localized infrared brightness. Without the spatial mapping, it would be impossible to connect the infrared light to the underlying molecular gas. JWST's high-resolution maps bridge that gap, showing exactly where the gas is hiding and how it produces observable signals. Signs of recent star formation. JWST didn't just detect molecular gas in the galaxy, it also found evidence that stars had formed relatively recently, in what was supposed to be a completely dead system. The first hints came from detailed spectroscopy using NIRSpec, which allowed astronomers to measure the light from stars directly. In the regions associated with molecular gas clumps, the spectra revealed features characteristic of young stellar populations, unlike the older red stars dominating the rest of the galaxy. Young stars emit differently from old stars. They are bluer and brighter in ultraviolet and optical light, although in high redshift galaxies, this light is shifted into the infrared. JWST, with its infrared sensitivity, was able to detect these subtle differences. The spectra showed slightly stronger Balmer absorption lines, as well as weak ultraviolet continuum in regions coinciding with molecular gas clumps. Both indicators are classic signs of stars that are not ancient, but relatively young, formed within the last few 100 million years. Age estimates for these young populations were striking. By analysing the spectra, astronomers concluded that the stars were tens to hundreds of millions of years old. This is very recent on cosmic timescales, especially compared to the rest of the galaxy, where the bulk of stars formed billions of years ago. The galaxy had been classified as quiescent because most of its stars are old, but JWST revealed that small pockets of star formation had continued long after the supposed quenching event. These findings directly contradict earlier timelines for galaxy evolution. Standard models predicted that quiescent galaxies at this redshift should have stopped forming stars abruptly after a rapid starburst, then entered a long passive phase. Any residual star formation was expected to be negligible. JWST's detection shows that star formation didn't stop completely. Instead, it continued at a low level, concentrated in small regions for hundreds of millions of years after the main burst. Previous telescopes had missed this activity for several reasons. Dust obscuration is one of the most important. Young stars are often embedded in molecular clouds, where gas and dust absorb much of their ultraviolet and optical light. In optical images, these regions appear dark, masking star formation from view. JWST's infrared instruments can see through dust, detecting light emitted from stars that would otherwise remain hidden. Wavelength limitations of older telescopes also contributed to the non-detection. Hubble and ground-based observatories are sensitive primarily to visible and near-infrared light. At high redshift, the light from young stars is redshifted into longer infrared wavelengths that these instruments cannot measure effectively. JWST, designed for deep infrared observations, captures this light directly, allowing astronomers to detect stellar populations previously invisible. Resolution at high redshift is another factor. At billions of light years away, even relatively large structures in galaxies appear very small. Ground-based telescopes and Hubble lack the resolution to separate individual star-forming clumps from the surrounding old stellar population. JWST's higher resolution and spatial mapping allowed scientists to identify small pockets of young stars within the galaxy. These clumps are faint and compact, easily blended with older stars in previous surveys. Selection bias in galaxy surveys also played a role. Earlier studies targeted galaxies based on optical colours, smooth light profiles, and lack of emission lines. Galaxies that appeared red and featureless were automatically classified as quiescent. JWST shows that this method misses subtle, low-level activity. Even in galaxies that seem dead at first glance, young stars and molecular gas can persist in hidden regions. The result is that previous surveys systematically underestimated star formation in quiescent galaxies, particularly at high redshift. The spatial correlation of young stars with molecular gas clumps provides additional evidence. Regions where JWST detected molecular gas and faint emission lines coincide with areas showing young stellar populations. This makes sense physically. Stars form from dense, cold gas, and their presence explains the localized emission lines and infrared light. The young stars are not distributed uniformly, but concentrated where the gas survives, producing structured signals that previous instruments could not detect. JWST also revealed the relative contribution of young stars to the galaxy's overall light. Although the majority of the galaxy remains dominated by old stars, these recent populations contribute enough luminosity to create detectable features in the spectrum. Balmer absorption lines, weak ultraviolet continuum, and localized infrared brightness all indicate that star formation persisted at a low but measurable level. The age estimates of tens to hundreds of millions of years are important because they define a timeline for ongoing activity. Standard models assume that quiescent galaxies enter a passive phase shortly after a rapid quenching event. In this galaxy, JWST shows that small-scale star formation continued long after quenching, challenging the assumption that dead means completely inactive. These young populations demonstrate that the end of a galaxy star formation can be gradual and uneven, rather than sudden and uniform. JWST's spatially resolved mapping also helped identify differences between clumps. Some molecular gas pockets host slightly younger stars, while others appear to have no recent formation at all. This variation shows that star formation is localized and patchy, not uniform across the galaxy. It also explains why the galaxy was previously classified as dead. When averaged over the whole system, the light is dominated by old stars, masking the low-level activity in small regions. Dust plays a central role in hiding this activity. Young stars embedded in molecular gas clouds are heavily obscured, absorbing their light in the optical and ultraviolet. JWST's ability to penetrate dust in the infrared revealed the stars directly. Without infrared sensitivity, their presence would remain invisible. This demonstrates why JWST is transforming our understanding of galaxies previously thought inactive. The detection of young stars also explains the emission lines observed earlier. Hydrogen recombination lines and ionized oxygen lines appear in the same regions as molecular gas and young stellar populations. Ultraviolet radiation from these relatively young stars is sufficient to ionize the surrounding gas, creating the emission lines. This direct link between gas, stars, and emission shows a self-consistent picture of ongoing localized star formation in a galaxy classified as dead. Previous optical and near-infrared surveys lacked the combination of sensitivity, resolution, and wavelength coverage to detect these features. Low-level star formation in clumps only a few hundred light-years across would have been invisible. The galaxy's overall red color, smooth profile, and weak optical emission lines led astronomers to assume complete inactivity. JWST reveals that these assumptions were incomplete. Even galaxies classified as quiescent can host recent star formation in hidden pockets. The young stellar populations also provide insight into the galaxy's quenching history. The fact that star formation persisted for tens to hundreds of millions of years after the main burst indicates that quenching was not instantaneous. Feedback mechanisms such as AGN activity, supernova, or environmental stripping may suppress star formation efficiently on a global scale, but pockets of molecular gas can survive. These surviving clumps allow sporadic or low-level star formation long after the galaxy's main quenching event. The spatial distribution of these young stars aligns with molecular gas clumps, emission lines, and infrared light. This demonstrates a direct connection between gas survival, ongoing star formation, and observable emission, which previous telescopes could not resolve. Without JWST's ability to map these features across the galaxy, the signs of recent star formation would remain hidden in the glare of older stars. JWST also allowed astronomers to estimate star formation rates in these clumps. While the rates are low compared to active galaxies, they are non-negligible. Some clumps form stars at fractions of a solar mass per year, enough to maintain observable emission lines and infrared luminosity. This low-level activity explains the structured signals seen across the galaxy and highlights that quiescent galaxies are not entirely inert. Dust obscuration, high redshift, and spatial blending explain why previous instruments failed. Hubble and ground-based telescopes are sensitive primarily to optical light, which is heavily absorbed by dust. At high redshift, light from young stars is redshifted into the infrared, outside the detection range of many instruments. Additionally, the small physical size of star-forming clumps, combined with limited resolution, meant that faint activity was blended with the dominant light from old stars. JWST's capabilities removed these barriers, allowing direct detection of young stellar populations in hidden regions. Selection bias in previous surveys compounded the problem. Galaxies were chosen for study based on smooth red colours, weak emission lines, and overall morphology. Systems with faint, patchy star formation embedded in dust would automatically be classified as quiescent. JWST demonstrates that these selection criteria miss subtle, low-level star formation, particularly at high redshift, revealing a previously hidden component of galaxy evolution. Evidence of a hidden active galactic nucleus. JWST's observations revealed something else entirely unexpected: signs of a hidden active galactic nucleus, or AGN, buried deep in the galaxy. AGNs are powered by supermassive black holes that actively accrete matter, producing radiation across the electromagnetic spectrum. In active galaxies, these central black holes are obvious because they outshine the surrounding stars or produce strong emission lines. In this galaxy, JWST revealed a more subtle signature, a mid-infrared excess that could not be explained by stars alone. MIRI detected infrared emission at wavelengths longer than expected from old stars. The emission was concentrated in the galaxy's central region, suggesting a compact source of heat. The spectral shape indicated hot dust being heated by high-energy radiation, consistent with energy released from an AGN accreting material. The mid-infrared excess alone was not enough to confirm an AGN, but combined with other clues, it pointed strongly to a hidden central black hole quietly at work. Ionization signatures provided additional evidence. The regions closest to the galaxy's center exhibited high ionization lines, including doubly and triply ionized oxygen, neon, and sulfur. These lines require photons much more energetic than those produced by old stars or even low-level star formation. The ratios of these lines are typical of gas excited by an AGN rather than stellar activity. The spatial coincidence of high ionization gas with the central infrared source strengthened the case for a hidden AGN. JWST also allowed scientists to detect subtle variability clues, though over a limited timescale. By comparing exposures across different instruments and epochs, researchers noted slight differences in the mid-infrared flux. While the changes were small, they are consistent with the flickering behavior expected from material accreting onto a supermassive black hole. Older telescopes lacked the combination of sensitivity, wavelength coverage, and resolution to detect this weak signal, leaving the AGN effectively invisible until JWST. This AGN had remained hidden because it was obscured and faint. Previous optical surveys missed it due to heavy dust in the central regions, which absorbs ultraviolet and visible light. The emission lines produced by the AGN were weak relative to the galaxy's dominant old stellar population, and the spectral resolution of prior instruments was insufficient to separate AGN signals from surrounding stars. Only JWST's infrared capabilities and spatial resolution allowed the detection of these subtle, localized features. The AGN also plays a role in the interaction between the central black hole and the galaxy's gas. Traditionally, AGN feedback is considered destructive. The energy released by accretion heats or expels gas, shutting down star formation across the galaxy. Observations in local quiescent galaxies often support this view, showing that active black holes can blow out gas or maintain high temperatures in the interstellar medium, preventing molecular clouds from collapsing into stars. JWST data, however, suggests a more nuanced picture. In this galaxy, the AGN may not be destroying gas everywhere. Instead, its energy could be compressing gas in localized regions, contributing to the formation of the molecular clumps previously detected. Emission lines and infrared light are strongest in regions surrounding, but not directly at, the AGN. This spatial pattern indicates that energy from the central black hole may be triggering low-level star formation in nearby pockets, while the rest of the galaxy remains quiescent. The presence of young stars in regions near molecular gas clumps supports this interpretation. Radiation or weak outflows from the AGN could create pressure waves that compress nearby clouds, increasing their density just enough to collapse and form stars. The effect is subtle. It does not produce a global starburst, but allows localized star formation to continue even in a galaxy that appears dead on large scales. JWST's spectroscopic mapping shows that these AGN-driven effects are limited in scope. The central regions closest to the black hole show high ionization lines, but molecular gas and low-level star formation occur in clumps at some distance from the nucleus. This suggests that the AGN's influence is both destructive and constructive, depending on location and the local density of gas. The interplay between the central black hole and surrounding gas is more complex than the traditional AGN kills star formation everywhere model. Previous instruments lacked the ability to identify this subtle feedback. Optical telescopes cannot see through dust, and low-resolution spectra cannot distinguish weak AGN signatures from the light of old stars. Infrared telescopes before JWST lacked the sensitivity or spatial precision to separate the central source from surrounding stellar light. JWST combines all three advantages: sensitivity, spatial resolution, and mid-infrared coverage, allowing astronomers to detect both the hidden AGN and its effects on nearby gas. The mid-infrared excess alone is not enough to confirm star formation triggering, but when combined with molecular gas clumps, young stars, and emission line patterns, a clear picture emerges. The AGN is not dormant, but it is quietly influencing the galaxy in a way that allows pockets of activity to persist. Observed clumps of molecular gas and young stars correspond spatially to regions that could be affected by the AGN's energy output, consistent with theoretical predictions of localized triggering. JWST data also reveal a gradient in ionization. Gas closest to the AGN shows higher ionization levels, while more distant clumps have lower ionization but still show emission lines. This gradient is consistent with radiation pressure and outflow models. The energy from the AGN reaches nearby gas clouds, compressing them without completely ionizing or destroying them, creating an environment conducive to low-level star formation. Velocity mapping provides additional evidence. Molecular clumps near the central AGN show small shifts relative to the galaxy's center, suggesting motion consistent with mild inflows or compression. These dynamics indicate that the AGN's influence is not uniform. Some clumps are being affected, while others remain largely untouched, explaining why low-level star formation is patchy and localized rather than widespread. This finding challenges the traditional view of AGN feedback as purely negative. JWST shows that AGN can have both suppressive and triggering effects, depending on the distribution of gas, local density, and distance from the nucleus. The hidden AGN in this galaxy is an example of how black holes can quietly shape the evolution of galaxies without producing obvious large-scale starbursts or violent outflows. Spectral analysis of ionized lines confirms that the AGN is the primary source of high-energy photons. While some ionization could come from young stars, the strengthened ratios of lines like O3 and Ne3 indicate a harder radiation field than stars alone can produce. This identifies the central black hole as the energy source, not stellar activity. At the same time, the molecular gas and faint young stars near the clumps indicate that the AGN is influencing its surroundings in a constructive way, compressing rather than destroying. JWST's observations provide the first detailed look at this dual effect in a high redshift quiescent galaxy. Previous models and surveys assume that AGN feedback only removes gas or suppresses star formation, but the data show that AGN can also play a subtle, positive role, triggering low-level activity in localized pockets of gas. The combination of mid-infrared excess, ionization signatures, molecular gas clumps, and young stars all point to this dynamic interaction. The hidden AGN also explains some previously puzzling observations. Mid-infrared light, emission lines, and weak variability could not be accounted for by old stars or residual star formation alone. JWST revealed that these signals originate from the central black hole, which had been invisible in earlier optical and near-infrared surveys. Its presence ties together the previously separate discoveries. Molecular gas, emission lines, and low-level star formation all occur in regions influenced by the AGN. Other dead galaxies. Re-examined. JWST's discovery in this one galaxy sparked a wave of new observations targeting other quiescent galaxies. Researchers began to ask a simple but critical question. If one supposedly dead galaxy still harbors molecular gas, emission lines, young stars, and a hidden AGN, how many others are hiding similar surprises? High redshift ellipticals were the first to be re-examined. These galaxies, typically classified as dead based on optical surveys, have smooth, red profiles and weak emission lines. Hubble and ground-based telescopes had long confirmed their quiescent nature. But JWST's infrared sensitivity allowed astronomers to probe them in new ways. When NER-SPEC and MIRI were pointed at a sample of high redshift ellipticals, faint emission lines appeared in several targets, similar to the first galaxy. Molecular gas was detected in small clumps, often associated with weak infrared emission and localized star formation, just like in the initial discovery. Compact, massive galaxies, another category of supposed dead systems, were also examined. These galaxies are dense, with most of their stellar mass concentrated in a small volume. Previous models predicted that these galaxies quench quickly, using up or expelling their gas early in cosmic history. JWST revealed that even these compact systems can retain residual gas reservoirs, often organized in small clumps that had gone unnoticed in optical observations. The gas was cold, patchy, and capable of supporting low-level star formation, producing subtle emission lines consistent with those detected in the first galaxy. Astronomers began to recognize a pattern across data sets. JWST observations consistently showed three key features in galaxies previously classified as dead. First, patchy molecular gas clumps, sometimes near the center, but often in off-center pockets. Second, low-level star formation, evidenced by young stellar populations tens to hundreds of millions of years old. And weak AGN signatures, including mid-infrared excess, high ionization emission lines, or subtle variability. These features were not universal in all targets, but the frequency was high enough to suggest that a significant fraction of quiescent galaxies may have been misclassified. JWST's high spatial resolution and infrared coverage revealed activity that was invisible to previous surveys, indicating that galaxy quenching is not always complete. JWST's spatial and spectral mapping also allowed astronomers to identify structural similarities among these re-examined galaxies. Many high redshift ellipticals and compact massive galaxies showed clumpy distributions of molecular gas aligned with weak emission lines, often coinciding with faint infrared light. This repeated pattern reinforced the idea that residual gas and localized star formation are not unique to the first galaxy, but are a common feature in certain quiescent systems. Comparison with older data sets clarified why these signals had been missed. Optical surveys rely on colour selection, smooth morphology, and weak emission lines to classify galaxies as dead. Infrared surveys before JWST lacked the sensitivity or resolution to detect faint clumps of molecular gas or subtle mid-infrared excess. Hubble's near-infrared instruments could detect broad stellar light, but could not resolve sub-kiloparsec scale clumps or weak emission lines in high redshift galaxies. JWST removed all three limitations, enabling the detection of low-level activity hidden within the dominant old stellar populations. These findings led directly to what astronomers now call the population problem. If multiple supposedly dead galaxies show signs of residual molecular gas, low-level star formation, and hidden AGN, then the census of quiescent galaxies in the early universe may be inaccurate. Surveys based solely on optical light or low-resolution infrared data may overestimate the number of truly dead systems, because they systematically miss small-scale activity. The implications for galaxy population statistics are significant. Estimates of quiescent galaxy fractions at high redshift rely on optical colour selection, emission line absence, and smooth morphology. If JWST reveals that many galaxies still have molecular gas and faint star formation, then a portion of the galaxies labelled dead should be reclassified as partially active. This shifts our understanding of galaxy demographics and cosmic history. The population problem also affects calculations of the cosmic star formation rate. Quiescent galaxies were assumed to contribute almost nothing to the total star formation rate at their redshift. JWST observations suggest that low-level activity in these galaxies adds a previously uncounted component. While it is not enough to dominate the star formation budget, it is measurable and relevant, particularly for understanding the tail end of star formation in the early universe. Pattern recognition across JWST datasets strengthens this conclusion. In surveys targeting hundreds of quiescent galaxies, a substantial fraction, sometimes tens of %, shows residual molecular gas, weak emission lines, or low-level star formation. These features occur across galaxy types, high redshift ellipticals, compact massive galaxies, and even some transitional systems. The result is that the concept of a dead galaxy needs refinement. Many of these systems are not completely inactive, but partially alive in localized regions. The discovery also reshapes interpretations of galaxy evolution models. Previously, quenching was modeled as a sharp transition, rapid starburst, sudden gas loss, and passive evolution. JWST shows that quenching can be incomplete, leaving behind molecular gas and localized star formation for hundreds of millions of years. This explains why emission lines, young stars, and weak AGN signals appear in galaxies long after they were thought to have stopped forming stars. In addition, JWST highlights the heterogeneity of quiescent galaxies. Not all systems retain gas or low-level star formation, and the properties of surviving clumps vary from galaxy to galaxy. Some retain significant molecular gas in multiple clumps, while others have smaller, less active pockets. A GN presence also varies. Some galaxies show weak central black hole activity, while others appear truly dormant. This diversity indicates that quenching and post-quenching evolution are not uniform processes, but are influenced by galaxy mass, environment, and merger history. JWST's data also provides direct comparisons with simulations. Cosmological simulations had predicted that some galaxies might retain residual gas after quenching, but the scale, distribution, and density of the gas clumps observed are often larger and more structured than predicted. This shows that simulations may underestimate the survival of molecular gas and low-level star formation in quiescent systems, particularly at high redshift. JWST provides observational constraints to refine models of galaxy evolution and feedback. Taken together, these observations suggest that the early universe may contain more active pockets than previously assumed. While the majority of stars in quiescent galaxies are old, a measurable fraction of the population continues to form new stars in localized regions. Hidden AGNs and surviving molecular gas indicate that galaxy quenching is often partial rather than absolute, affecting both the classification of galaxies and the interpretation of cosmic star formation history. The population problem also emphasizes the importance of JWST's capabilities. Without high-resolution infrared imaging and spectroscopy, these subtle features would remain invisible. Optical surveys systematically miss dust-obscured clumps, small-scale star formation, and hidden AGNs. JWST's ability to detect and map these features changes the statistical picture of quiescent galaxies across cosmic time. Astronomers now recognize that the term dead galaxy may be misleading. While most stars in these systems are old and large-scale star formation is suppressed, JWST shows that small pockets of activity persist, sometimes supported by molecular gas and influenced by hidden AGNs. Re-examining other galaxies reveals that the phenomenon is not unique. A substantial fraction of previously classified dead galaxies may host low-level star formation and gas reservoirs, meaning the population of fully dead galaxies is smaller than previously thought. Timeline models are wrong and mass, gas, and feedback rewritten. JWST has forced astronomers to rethink the entire way we understand galaxy evolution. For decades, models of galaxy death were built on a straightforward picture. A galaxy forms stars rapidly, uses up or expels its gas, and then enters a long passive phase. Star formation stops, gas is gone, feedback shuts everything down, and the galaxy slowly ages. Simple, neat, one-way evolution. Observations from Hubble, ground-based surveys and simulations all reinforce this framework. The first crack in that model appeared with JWST's high-resolution infrared observations. Galaxies previously labelled dead showed molecular gas hiding in clumps, low-level star formation, and hidden AGNs. The simple idea of rapid quenching, the sudden stop of star formation followed by permanent inactivity, didn't match the data. Some galaxies still formed stars hundreds of millions of years after the supposed quenching. Others had pockets of gas that could potentially collapse into stars at any time. JWST showed that star formation in these systems is stop-start, patchy, and unpredictable, not a single, irreversible event. Models that assumed one-way evolution, from blue, active, star-forming galaxies to red, passive, dead ones, are now incomplete. JWST reveals that galaxies can retain fuel and episodically form stars long after they appear quenched. The hidden AGNs further complicate the picture. Instead of only shutting down star formation, some AGNs may compress molecular gas, triggering localized activity even in a largely inactive galaxy. A galaxy classified as dead on the outside can still have pockets of life inside, showing that quenching is not the end of evolution. Evidence for stop-start star formation comes from spatially resolved spectroscopy. JWST maps of molecular gas clumps show that some regions contain young stars, while others are completely inert. Age estimates from stellar spectra reveal that stars can form tens to hundreds of millions of years after the main population formed. This creates a timeline where star formation is intermittent, rather than a single burst followed by total quiescence. Observing multiple galaxies with JWST suggests this is not an isolated case. Many quiescent galaxies have similar stop-start patterns hidden beneath their red, smooth light profiles. Mass, gas, and feedback all have to be reconsidered. Stellar mass no longer tells the whole story. In previous models, a galaxy's mass predicted its ability to retain gas and resist quenching. JWST shows that galaxies with similar masses can have very different amounts of molecular gas remaining. Some massive galaxies still harbour dense gas clumps, while others have none. Mass alone cannot explain the observed diversity. Gas retention is more complex than thought. Molecular gas can survive in clumps for hundreds of millions of years after quenching events. These clumps can exist near the centre or in outer regions, sometimes shielded from feedback, sometimes influenced by weak AGN activity. The patchy distribution observed by JWST suggests that local conditions, internal structure and environmental factors play a critical role in determining where gas survives and how it behaves. Black hole activity is another key factor in the new picture. Previously, AGNs were seen as purely destructive. Energy from accretion heats or expels gas, shutting down star formation across the galaxy. JWST shows that AGNs can also trigger localized star formation by compressing molecular gas. The relationship between AGN energy output and molecular gas is dynamic and spatially dependent. Some clumps experience compression and low-level star formation, while other regions are cleared or heated. This dual role means that simulations must include both destructive and constructive AGN feedback, rather than assuming a single mode. The combination of mass, gas, and feedback creates a much more nuanced picture than traditional models allow. Gas-rich clumps can persist in high-mass galaxies, young stars can form long after quenching, and AGNs can both suppress and trigger activity. JWST's data indicate that galaxy evolution is not a simple one-way track, but a complex interplay of internal and external processes, which must be modelled in 3 dimensions and across time. Simulations must change to account for this new complexity. Traditional models often assume that once a galaxy is quenched, it remains so indefinitely. Gas is removed or heated, star formation stops, and the galaxy gradually ages. JWST data show that this assumption is incorrect for many high redshift galaxies. Simulations need to include patchy molecular gas survival. Not all gas is expelled or heated evenly, and there's localized star formation. Small pockets of young stars can persist in clumps. We also have AGN dual roles. Feedback can trigger star formation in nearby gas while suppressing it elsewhere. And stop-start evolution. Galaxies can experience multiple minor episodes of star formation after quenching. The new picture also affects the predicted cosmic star formation rate. If a significant fraction of galaxies previously classified as dead still form stars, even at low levels, then the contribution of quiescent galaxies to the total star formation rate must be updated. This could subtly adjust our understanding of galaxy evolution at high redshift, particularly in terms of when and how the universe transitioned from active star formation to widespread quiescence. JWST reveals that galaxy quenching is heterogeneous and incomplete. Different regions in the same galaxy can have completely different histories. The core may be dominated by old stars with a weak AGN. Outer clumps may host young stars, and molecular gas may survive in both locations. Observing multiple galaxies confirms that this is not a single anomaly. The stop-start nature of star formation and patchy gas distribution appears in many high redshift ellipticals and compact, massive galaxies. Stellar mass, gas content, and AGN activity are intertwined in ways that traditional models did not capture. Mass alone does not determine the survival of gas, and AGN activity can have both positive and negative effects. Gas clumps can persist for hundreds of millions of years, producing young stars and emission lines that were previously invisible. JWST's high-resolution spectroscopy and imaging provide a three-dimensional, dynamic view of quiescent galaxies, challenging the simple, linear evolutionary pathways used in older simulations. The combination of these factors means that quenching is a process, not an event. It occurs over hundreds of millions of years, influenced by the distribution of molecular gas, the location of young stars, and the activity of the central black hole. Observed galaxies may appear dead in optical light, but remain active in hidden pockets, producing faint infrared emission lines, and young stars detectable only with JWST. JWST data also reveal correlations between molecular gas, stellar mass, and AGN presence. Galaxies with larger stellar mass tend to retain clumps of gas longer than smaller systems, but exceptions exist. Some low-mass galaxies still host dense gas pockets, while some massive systems are truly quenched. A GN feedback can either accelerate gas loss or trigger localized star formation depending on its energy output and proximity to surviving gas clumps. The interplay between these factors produces diverse evolutionary pathways, which are only now being revealed thanks to JWST. JWST also forces astronomers to rethink the very definition of a quiescent galaxy. Instead of assuming dead means completely inactive, the data suggests that quiescent galaxies may contain pockets of life, including molecular gas, young stars, and hidden AGNs. Galaxy evolution models must account for this complexity, including heterogeneous star formation, patchy gas survival, and nuanced AGN feedback, to accurately describe the history of galaxies across cosmic time. What JWST will target next. The first reactions to JWST's findings were intense. Scientists around the world had spent decades building a framework for galaxy evolution. And here was a single galaxy, supposedly dead, defying all expectations. Initial reactions in seminars and online discussions range from disbelief to cautious curiosity. The presence of molecular gas, faint emission lines, low-level star formation, and a hidden AGN in a quiescent galaxy seemed almost impossible under the standard models. Many wondered if the data might be contaminated, misinterpreted, or the result of calibration errors. Independent teams quickly prioritized verification. Using the same JWST data, researchers repeated the analysis, focusing on spectral lines, infrared flux, and spatial distributions. Their results confirmed the initial findings. Molecular gas clumps, weak hydrogen, and oxygen emission lines, and young stellar populations were real, not artifacts. Spatial mapping using NIRSpec and MyRE reinforced that these features were localized and correlated with hidden AGN signatures. The independent confirmations turned initial skepticism into acceptance of a radically new observational result. Peer-reviewed papers began to appear, analyzing these quiescent galaxies in detail. Each study added a layer of nuance. Some emphasized the patchiness of molecular gas, showing that clumps are often small, dense, and unevenly distributed across the galaxy. Others highlighted the stop-start nature of star formation, demonstrating that young stars can form hundreds of millions of years after the main quenching event. Several papers focused on hidden AGNs, showing that mid-infrared excess, ionization gradients, and weak variability could explain previously puzzling emission lines. Together, these studies painted a consistent picture. The simple idea of a completely dead galaxy is no longer sufficient. Some debate still remains. Questions center on the prevalence of these features across the galaxy population. How many quiescent galaxies retain molecular gas? How often do hidden AGNs trigger localized star formation? Are low-level star formation rates consistent across environments, or do they depend on galaxy mass, merger history, or cosmic location. Different models predict different outcomes, and JWST's early results are beginning to constrain these possibilities, but have not yet resolved all uncertainties. Another topic of discussion is feedback mechanisms. Observers agree that AGNs can suppress star formation, but the degree and spatial pattern of suppression remain debated. Some researchers argue that AGNs may predominantly destroy gas, while others suggest that local triggering occurs more often. JWST's data show both effects in the same galaxy, but understanding how common this is across populations requires larger surveys. Despite these debates, the overall reaction is one of excitement. JWST has provided unprecedented insight into galaxy evolution, revealing processes that were invisible before. Scientists are now revising textbooks, updating models, and designing new simulations to match these findings. The consensus is that galaxy death is not uniform, irreversible, or absolute. It can be gradual, partial, and influenced by both internal and external factors. With these discoveries, JWST's observing strategy is shifting toward follow-up and expansion. One key goal is to observe more quiescent galaxies across a range of redshifts. Researchers plan targeted surveys to measure molecular gas content, low-level star formation, and hidden AGNs in hundreds of galaxies, testing how common these features are. By comparing galaxies at different distances and ages, astronomers hope to build a statistical understanding of quiescent systems and determine whether JWST's initial findings are typical or rare. Spectral deep dives are another priority. Instruments like NIR-SPEC will be used to capture high-resolution spectra of molecular gas and young stars, revealing the detailed physics of these pockets. Scientists want to measure gas density, temperature, metallicity, and ionization states, connecting these properties to star formation efficiency. Mid-infrared spectra from MEARI will probe dust properties, AGN heating, and obscured star formation. JWST's combination of sensitivity and spectral resolution allows researchers to study these galaxies in unprecedented detail, separating overlapping signals and mapping gas, stars, and black holes across space. Scientists are also planning temporal observations, looking for variability in AGN activity or star formation signatures. Repeated observations over months or years can reveal flickering AGNs, short bursts of star formation, or subtle shifts in emission lines. These measurements will help constrain feedback mechanisms, showing where AGNs suppress gas and where they may trigger star formation. Statistical surveys are being designed to answer broader questions about the galaxy population. JWST will observe quiescent galaxies in different environments, clustered regions, isolated systems, and merging galaxies, to determine how gas survival and low-level star formation depend on surroundings. By building large datasets, researchers aim to reassess the fraction of truly dead galaxies at high redshift, updating cosmic star formation rates and improving models of galaxy evolution. Another target area is extreme quiescent systems, including the most massive, densest galaxies in the early universe. JWST will probe these objects to see if they also harbour hidden molecular gas, or AGNs, testing whether the phenomena observed in more typical quiescent galaxies scale with mass. These observations will clarify the role of galaxy mass in determining gas retention, star formation persistence, and black hole influence. JWST will also revisit previously studied galaxies with known AGNs to compare feedback effects. Are mid-infrared excesses and emission line patterns similar across multiple systems? How does AGN luminosity correlate with gas compression or suppression? These follow-ups will refine our understanding of AGN influence, providing the first clear empirical constraints for simulations that include both constructive and destructive feedback. Finally, JWST will explore transitional galaxies, those on the border between star forming and quiescent. These galaxies may hold clues about how quenching begins, how gas is redistributed, and how AGN feedback triggers or suppresses localized star formation. Observing these systems in the same detail as fully quiescent galaxies will help connect the stop-start patterns observed in older galaxies to the early stages of galaxy death. JWST's next campaigns are ambitious. Scientists want to prove or disprove whether the patterns seen in the initial dead galaxy, molecular gas clumps, low-level star formation, hidden AGNs, are universal. They aim to map hundreds of quiescent galaxies across space and time, measure physical properties in detail, and build a statistically robust picture of how galaxies actually quench, evolve, and interact with central black holes. JWST is not just confirming previous models, it is actively rewriting them, targeting the unknown corners of galaxy evolution that were invisible before. Every new observation has the potential to reveal another exception, another hidden pocket of life, and another way in which quiescent galaxies are far more complex and dynamic than anyone imagined. Why the term no longer works. The term dead galaxy was always convenient. Astronomers needed a simple way to categorize galaxies that weren't forming stars and had mostly old stellar populations. Quiescent became the technical label, a galaxy that shows little or no star formation, weak or absent emission lines, and smooth red colors. In textbooks and surveys, quiescent galaxies were assumed to be the endpoints of galaxy evolution, the final stage after rapid star formation and quenching. JWST's findings, however, make the term dead inaccurate. The galaxy at the center of this discovery was classified as quiescent, based on optical data, smooth morphology, and red color. Hubble and ground-based telescopes saw no blue light, no dust lanes, no active nucleus, and therefore no reason to question its status. JWST revealed the truth. This galaxy was never completely inactive. It has molecular gas clumps, low-level star formation, and a hidden AGN. Star formation is happening, even if intermittently, and gas reservoirs are surviving in regions that should have been cleared long ago. Because of this, astronomers are reconsidering the language used to describe such galaxies. Quiescent suggests a permanent state, when in reality these systems can be intermittent. Star formation may stop in some regions but restart in others. AGNs may suppress gas in one location while triggering star formation nearby. Dormant has been suggested as an alternative, implying that activity can resume if conditions allow. Some researchers now favour terms like partially active or intermittently star forming to capture the patchy and dynamic nature revealed by JWST. Classification systems will need revision. Traditional optical surveys relied on smooth morphology, red colours, and weak emission lines. These criteria fail to detect localised molecular gas, faint emission lines, or mid-infrared excess from hidden AGNs. JWST observations suggest a more nuanced scheme. Galaxies should be classified not only by total star formation, but also by the presence of molecular gas, young stellar clumps, and AGN signatures. This means a galaxy previously labelled quiescent could now fall into a hybrid category, where the bulk of stars are old, but pockets of activity persist. Astronomers are proposing multi-layered classification systems that combine stellar population age, gas content, star formation activity, and AGN feedback. Galaxies could be labelled based on the fraction of mass actively forming stars, the density and distribution of molecular gas, and the presence or absence of AGN influence. This system acknowledges that galaxies are complex, evolving systems, not static objects that neatly fit into two bins of active or dead. JWST's observations provide unambiguous evidence that this galaxy was never truly dead. Molecular gas clumps detected with NIR-SPEC and MIRI exist throughout the galaxy in patchy distributions. This gas is cold, dense, and capable of forming stars. The young stellar populations detected are tens to hundreds of millions of years old, meaning star formation persisted long after the galaxy was classified as quiescent. Star formation in quiescent galaxies is not only possible, but ongoing in small, localized regions. JWST shows that these pockets of activity can be hidden beneath red, smooth stellar light. They are invisible in optical surveys and even in previous infrared observations without sufficient spatial resolution. What was assumed to be complete quenching is in reality partial quenching, leaving behind the fuel for future star formation. Molecular gas can survive quenching. In this galaxy, JWST maps reveal clumps of cold gas that persist hundreds of millions of years after star formation was thought to have ceased. These clumps are shielded from feedback, dense enough to resist heating from AGNs, and capable of sustaining new star formation. This overturns the standard idea that quenching removes or heats all gas to prevent star formation entirely. A GN behavior is more complex than assumed. Previous models treated AGN feedback as a largely destructive force, shutting down star formation across the galaxy. JWST observations show a dual role. RGNS can suppress star formation in some regions while compressing gas and triggering star formation in others. Mid-infrared excess, high ionization emission lines, and subtle variability confirm that the AGN is active and influencing its surroundings in nuanced ways. Feedback is spatially dependent, intermittent, and context-sensitive. The combination of these factors means the basic assumptions of galaxy death are being rewritten. Galaxies previously labeled as quiescent cannot be treated as fully inactive. Some regions form stars, molecular gas survives, and AGNs act in complex, sometimes constructive ways. JWST's data provide the first clear observational evidence of this, directly challenging decades of theory. This galaxy fundamentally changes how scientists think about galaxy evolution. Theories based on rapid quenching, one-way evolution, and permanent inactivity must be updated. Stop-start star formation, patchy gas survival, and dual-role AGN feedback are now essential components of galaxy evolution models. It also affects early universe models. Quiescent galaxies were assumed to be entirely inactive at high redshift, shaping calculations of cosmic star formation rates and the evolution of stellar populations. JWST demonstrates that these assumptions are incomplete, revealing a population of galaxies that retain activity long after supposed quenching events. Star formation rates, gas fractions, and AGN feedback models must all be revisited in light of these observations. This discovery proves that JWST is not just a clearer telescope. It does more than see galaxies in better detail. It reveals fundamental incorrect assumptions that have persisted for decades. By detecting hidden molecular gas, low-level star formation, and subtle AGN signatures, JWST exposes the complexity of galaxies that were once assumed to be simple, dead objects. Every observation has the potential to overturn a piece of long-standing theory. JWST also opens a path for future research. Understanding intermittent star formation, gas survival, and AGN influence will require targeted surveys, spectral deep dives, and statistical studies. Observing multiple galaxies across cosmic time will reveal whether this system is unique or part of a larger population, and will clarify the role of mass, environment, and feedback in shaping galaxy evolution. The redefinition of quiescence is already underway. Astronomers are moving toward dynamic, multi-parameter classification systems that recognize galaxies as evolving, heterogeneous, and sometimes partially active. JWST has forced this shift, providing the first detailed, high-resolution evidence of processes that were invisible in optical surveys. The term dead galaxy no longer accurately describes these systems, and the new language will reflect the true dynamic complexity of galaxy evolution. JWST has shown that even in galaxies where most stars are old, molecular gas can survive, low-level star formation can occur, and AGNs can act in unexpected ways. These insights rewrite the narrative of galaxy death and highlight the importance of infrared, high-resolution observations in revealing the hidden activity of the universe. Every quiescent galaxy may contain secrets waiting to be uncovered, and JWST is the first telescope capable of exposing them in detail.